I'm saying I don't have YouTube.
No. I like that. Okay. Whatever I do, you listen and you write because the papers are really bad. Okay, so you just have to. You could give it to us and pay subscribe. No. Tomorrow I will not say. Okay. So yesterday we did. Yesterday the last thing we stopped is we were starting the mechanical properties of liquid. You remember? We started mechanical properties of liquid. In mechanical properties of liquid, we started with the difference between streamline and turbulent flow. Okay. Now, why did I teach you that when streamline and turbulent flow is? I said for every theorem, for any equation like equation of continuity, all one clause is coming for a streamlined motion. It's not true for a turbulent motion. Okay. So when a liquid flows in a streamlined way, then only you can explain all these things what we are doing. Turbulent, there are rules and other things involved in that. Okay. So here also we are going to study an equation. It's a very, very simple equation. You listen carefully, you can understand. Are you reached? Sit there. Here you can sit. Here, not you can sit. One sit there, one sit there. You come here, sir. Okay, so streamline we did that. Equation of continuity is a very simple equation. It's not a complicated one, but small steps are involved. So when I teach, if you have any doubt as I go forward, raise your hand, we'll clear it and then go forward. Don't think later I'll ask. It will be difficult. Okay. So what is meant by equation of continuity? To understand equation of continuity, we see the same figure we saw yesterday. You remember this figure? What was this combination of streamlines called?
A spring tube.
Tube of flow. Okay. So tube of flow is a group of streamlines. So we have 4 streamlines here. That is the path of the particle which will take in a flow of liquid. So consider the streamline flow of. So this is the condition for even explaining or starting equation of continuity. This is the condition. What is condition? Consider the streamline flow. You are not considering the turbulent flow. Consider the streamline flow of incompressible. The liquid that you take in the tube is incompressible, non-viscous. I told you approximately yesterday the meaning of viscous and non-viscous. We'll see in detail what is viscous and non-viscous. Understand viscosity as the thickness of a liquid. So you're taking a liquid like which has least thickness, or the it's a something like a water thing which has low viscosity, and it is incompressible and it is a streamlined flow. Consider it passing through a pipe of non-uniform cross-section. You are not taking a pipe like this. You're not taking a pipe of uniform cross-section. You're taking a pipe of a bigger cross-section and a smaller cross. It's a non-uniform cross-section. Clear what is that? What we're trying to say? First paragraph. Next. Consider 2 areas. So we are considering one area of cross-section A, another area of cross-section B. How is the area of cross-section's direction in the direction of the flow of water? What is in area of cross-section is like this. The tube is like something like this, you imagine. Okay, this is there. This is a sphere. This is a circle thing. So if this is a tube, if you see the area of cross-section, it is like this. Water is like this. What's the direction between direction of flow and the area of cross-section? It's perpendicular. So that's what they're trying to tell you. Consider 2 areas. Now here areas here means area of cross-section A and B. Okay. So consider 2 areas A and B. How is A and B? They are at right angle to the direction of flow of liquid. Just now you told me flow of liquid is like this, but area of cross-section is like this. So consider 2 areas A and B at right angle to the direction of flow of liquid. Then what you have to do? Draw a streamline. We are drawing the streamlines. Then a tube is obtained which is called. So that's nothing much to understand in this slide. Only to understand that you have taken a non-uniform cross-section tube. A and B are the area of cross-section. This is a streamline. A group of streamlines is called tube of flow. The liquid that you take inside the tube is incompressible, streamlined, non-viscous liquid that you have taken inside the tube. Clear this much? How it is? Yeah. Now, yesterday, according to what we discussed yesterday, before we go to the second slide, when the area of cross-section is more, what can you tell about the velocity of liquid? Yes, yesterday we saw that. So, area more, V, yes, that we saw. Area of cross-section is more. So here, where is the velocity more? At A or at B?
At B.
At B. That is where we start. Okay. Now, Now, what is the volume of liquid entering the area A per second? So, here what they are trying to do is, we are calculating volume per unit time. So, we saw the big tube like this going. Okay, this is, which was A and which was B? A was the bigger one, B was the smaller one. Okay. So, A is here and B is here. Okay. So, liquid is going like this. Okay. What is the volume of liquid entering A per unit time? What is the volume of liquid entering the area of cross section per unit time is what I am trying to calculate. So, what is volume by time? Volume of the tube. Volume of the tube is area of cross section into the length of the tube. Correct? To take a cylinder, if you take like this, what is the volume of that cylinder? Volume of the cylinder can be written as area of cross section into the length, A into L. Yesterday also reduced that. Okay. So, volume can be written as area of cross section into this length. Okay. Divided by that, which is equal to area of cross section. What is length by time? Distance by time. Velocity. So, if V1 is the velocity here and A1 is the area of cross section, and A1, V1 is the volume of liquid entering A. Is the volume of liquid. Have you used A1? Yeah. They have used A1. Yeah, A1, V1 only. So we have, this is A1, A2, this is V1. So what they are telling is, let the area of cross section be A. The area of cross section is A1 here. Velocity of liquid here is V1. Area of cross section is A2 here. Velocity is V2. How much is the volume of liquid entering this area of cross section A? It is area of cross section A1, correct? Area of cross section we call by A1 into the velocity of liquid, which is V1, correct? So volume per unit time is area of cross section into velocity. Have you understood how we came?
No, I just have one question. Here the section A, which is its thickness is 0, right, ma'am? It's just a cross section.
Which one? A?
Now the section A, the thickness is 0, right, ma'am?
It is?
The thickness of the
Yes,
section
yes,
is 0.
yes. Thickness is 0. It's just area of cross section.
Ma'am, so the length is here.
No. This length is coming from volume of liquid entering. See here. This is volume of liquid entering the tube.
Yes, ma'am.
So this tube's volume is only area of cross section into length.
Yes, ma'am. But what is this length?
What is?
Now, what is this length?
Length of the tube. Volume of liquid entering the tube.
Yes, ma'am.
So here the length is length of the tube. Not the length of the area of cross section. There is no length there.
Yes.
See, if you take cylinder like this, what is the volume of this?
Yes, ma'am. That's for the entire cylinder. But we are if I said a cross section, right, ma'am?
No. We are talking of A. A is only the cross section.
Yes, ma'am.
We are talking about A only. B is the volume of liquid entering the tube.
Yes, ma'am. It's not about liquid passing through the cross section.
No. See, volume, it has to pass the area of cross section to enter the tube.
Yes,
that is there. But this B is equal to air is coming from the tube, not from the area of cross section.
Yes, ma'am. But we don't know about the rest of the tube, right, ma'am?
Yeah?
Ma'am, we don't know about the rest of the tube. We only know about that area of cross section.
No, we know the length of the tube. We are taking the length of the tube. How much it has to pass through the whole tube. At least to the length A2 is reached. For example, suppose you take this as one tube. This will be the L. And this is the volume of the tube. And this is the area of cross section.
Yes, ma'am.
Because so the cylinder have to be, the tube will have to be uniform throughout.
No, till here only we take. At
Yeah,
present.
so, yes,
Yeah,
so till
till
there-
here it is uniform. See here how the tube is.
Ma'am, but what if it isn't uniform to there? What if it changes?
See here, till here. Then you can take this as another part. You got it?
Ma'am, but what if it's infinitely varying? Like it goes like this and this and this.
Then you can't take that.
Yes, ma'am. So I think that formula will be a little long. Area and length by time.
No. See here. We'll see.
Ma'am, we can still take area.
See, here they are just saying volume of liquid entering the section A per second.
Yes, ma'am.
So volume of the liquid is area into length. Which is the other length we can talk about if you don't take the
We
length
don't
of
need
the
to
tube.
talk about length. We can also understand formula area and velocity and have this cross-sectional area. And
Length will be what?
no, I don't think we need that, ma'am.
No, you need that. How will you get that equation A1 B1 without that?
Yes, ma'am. So we got this cross-sectional area,
Hmm.
and we know there's water coming from somewhere, enter it and leave it.
Ah.
And if we know a time interval,
Ah.
the velocity tells us how fast water is going. So we know how much volume of water can go through that.
Maybe there's another way of doing that, but maybe at your level they want you to do like this one.
Yes.
That way also you can do. So here, look here, one second. Volume of liquid entering the tube. Okay, volume of liquid entering the tube is, volume is area of cross section into the length by the time. Length by time is velocity. So basically you have to understand how much volume of liquid is entering A is exactly equal to area of cross section into the velocity of liquid at the point A. Go to the other side. If you see this side, what will be the volume per unit time for that? How much is the volume of liquid entering this part of the tube?
A2.
A2 will be equal to A2. Is it clear this much? Yeah, A1, B1 and A2, B2 will come back. So here, the volume of liquid entering the section A per second. So basically you are calculating volume by time. Volume is area into length, length by time is velocity. Okay. So A1 into B1. Same thing if you do for the other. How much is the volume of liquid leaving the tube? It will be A2, B2. So one you got A1, B1 and the other one is A2, B2. So I'll just read out. The volume of liquid leaving per second is A2, B2. Where A1, A2 and B1, B2 are area of cross section and velocities of section A and B respectively. Just now we saw that. Since the liquid is incompressible, the density of liquid, now you have to understand, the liquid is incompressible statement says that the density of liquid entering here is same as the density of liquid leaving from here and going to this tube. Okay, the density of the liquid is not changing. So what's the density here? Rho of the liquid, here also will be density rho. But when we do the equations, initially we take, let rho1 be the density of the water entering at A and rho2 be the density of liquid leaving B or entering the B section. What can you tell about rho1 and rho2? Yeah. So if you want, you can see later. See here. They add that statement. For an incompressible liquid, rho1 equal to rho2. So don't get confused because in this, or if it is difficult, don't even learn rho1, rho2. Just learn it as A1, B1, rho is equal to A2, B2, rho. Here what they have done is they put it as A1, B1, rho1 equal to A2, B2, rho2, and then they have later told that okay, rho1 and rho2 are equal because the liquid is incompressible. So that is what this is. So basically nothing much is here. We're just trying to say that. And in this section, the very important thing, if you have a tube of two variable different cross section, let A1 be the cross section here and A2 be the cross section here. Velocity of liquid entering this is V1, velocity of liquid entering leaving this is V2. Then volume of liquid, total volume of liquid entering per second here is A1, V1, and total volume of liquid leaving here is A2, V2. Okay. Now how water which enters has to leave. So what can you tell about A1, V1 and A2, V2? They have to be equal. So this is the volume by time. And this is also volume by time. Suppose I multiply a density here. What will you get the quantity?
Mass by time.
Mass by time. Volume by time into density. Volume by time into density. What do you get if you do volume into density? Mass. So what is the quantity A1, V1, rho actually equal to? Mass per unit time. Mass of water entering the tube and mass of water leaving the tube. So what does this equation say? It says that volume per unit time entering the tube and leaving the tube are same, and hence the mass of liquid entering and leaving the tube are also same. That mass per unit time is called mass flow rate, and volume per unit time is called volume flow rate. So there are names for that. Is the basic theory clear to you? Now what happened to rho? Both are same. So what is the final equation? This is only equation of continuity. That's all. So A1 V1 is equal to A2 V2. Where A1 and A2 are the area of cross section of the two ends of the tube, and V1 and V2 are the velocity. Because we know when the area of cross section changes, the velocity has to change. Clear this much? Yeah, we'll go back to the slides. What are the other things? Basic idea is only so much. Just look at the slide. This slide is clear? It's clear? Yeah.
Where no liquid can cross the side is basically
No liquid can cross the side means you cannot have a pipe with here water entering in, here entering in all. One entry point and one exit point. Then only this whole thing is true. You cannot make water entering here and another water entering here and both combining and going. Then this doesn't work. Okay. So the whole tube, one entry and one exit. Water is the water entering the tube has to be the same water which is leaving the tube. The total volume per unit time entering is equal to total volume leaving. Total mass entering is equal to total mass leaving. So we'll just quickly go through this. I'll ask one of you, 2-3 people to read. As they read one paragraph, if anyone has a doubt, you can ask. Partha, read clearly.
It is there.
Sir.
Yeah, I don't know.
She's telling you to remove it.
I have to go 5 minutes ago.
No, he has left it in front of the gate.
Which gate?
The ground gate. Thank you.
The volume of liquid and
Wait. Wait. You can go back. Leave it like this.
If there's no pause over there, that's a stop. Just pass that like. Actually, you can just stop it.
Why do you want to take it?
Rahul wants to.
Ma'am, because you cannot see the thing from the.
Everything go back.
There's no pause on my phone.
No, you can't see, ma'am. It's fine.
Can I increase the height of this?
Yeah, please move.
Spin this thing.
The way you said.
That's enough.
Yeah, Father start reading. Father will read one paragraph. Any point in that as he reads, if you have doubt what you have explained apart from that, just raise your hand and explain. Yeah, continue.
volume of liquid entering A per second is equal to A1 V1, which is basically volume by time, which is equal to area into length by time, which is basically area into velocity. The volume of liquid leaving section B per second is A2 V2, where A1 and A2 and V1 V2 are the areas of cross section and velocity is section A and B respectively. Since the liquid is incompressible, the density of liquid at A and B will be equal. The flow is steady. No liquid can cross the side, so the mass of liquid passing through section A is equal to the mass of liquid passing through section B in 1.
No liquid can cross the side. That is, you cannot have an entry point and then liquid going off like this and going off in parts like that. Okay, other than that is safe. Now, yeah, I will.
A1 V1 ρ1 is equal to A2 V2 ρ2. The mass of fluid flowing through a tube per second is called mass flow rate. The equation of
Okay, that's not there.
thus at every place in the tube, the product of the area of cross section of the tube and the velocity of flow of the liquid is a constant. Therefore, the velocity of the liquid is smaller in the wider parts of the tube and larger in the narrower parts.
That is the main theory. If you have a tube which has one bigger cross section and a smaller cross section, bigger cross section will have lesser velocity. Smaller cross section will have greater velocity. This yesterday also we have seen, but here in the top of the equation we will see. Now this is what will come for exam. Nobody is going to ask you any of these. Okay, no figure, this and all. Nothing will come in the exam. What will I ask? What will I ask is defines equation of continuity. Give the equation. Define equation of continuity. Give the equation. And this is the proper definition. So this is the equation of continuity, and this is the equation. That's all. This much is what we come for exam. And this may be asked. What conservation is happening here? Mass, no? How much mass of liquid is entering the tube has to leave. Mass cannot disappear from the tube. So how much liquid mass is entering the tube? That much mass of liquid is leaving the tube. So here it expresses law of conservation of mass. Okay. So this is the statement. Yeah, read out Mahika.
The equation of continuity states that the mass flow rate has the same value at every position along the tube, which has only one entry point and a single outlet for the fluid flow. This equation is called equation of continuity. A1 V1 is equal to A2 V2.
So mass flow rate has the same value, means what? Total mass of liquid entering the tube has to be same as total mass of the liquid leaving the tube. That's the meaning. Mass flow rate is another word for mass entering the tube per unit time or per second. Okay. So SI unit is this, unit is kg per second, mass per unit time. Now here they again say, okay, how did we get that rho 1 became equal to rho 2? So A1 to so we're getting confused with this rho 1 rho 2 business. Don't do in the beginning itself, you write up A1 V1 rho is equal to A2 V2 rho, rho and rho cancel. So A1 V1 is equal to A2 V2. Yeah. Now this A1 V1 is what? What is A1 V1? Volume per unit time. Okay, so that is written right down here. Okay, this all will come again. So A is more, then B is less. Okay. Now volume per unit time is called, what is the name given here? It's called volume flow rate. Volume flow rate. And mass per unit time is, what is it called? It's called the mass flow rate. Any doubt here? Clear? Yeah? So that's what they're talking about, this volume flow rate. This A1 V1 is nothing but volume of liquid flowing per second, and it's called volume flow rate. And same thing, the area of cross section is small, velocity is larger, the SI unit is meter cube. So what is the unit of volume per unit? What is the unit of volume?
Meter cube.
What is the unit of volume?
Meter cube.
Per second is the unit of volume. What is the unit of mass?
Kg.
Kg per second is the unit of mass. Clear? Yeah. Now we'll go to the next one. It's called Bernoulli's theorem. It's one of the most important.
Yeah. So to find V by T or M by T, you use the A1 V1.
See, to find V by T is directly equal to A1 V1. Same thing in mass flow rate is equal to A1 V1. So this is volume. This is volume into density. That's only difference. Okay. Here, no need to talk about rho 1, rho 2, rho you can see. Now, Bernoulli's theorem derivation is a little long derivation and it's a little complicated derivation, but you try to understand. It can come for exam. Statement of Bernoulli's theorem, equation of Bernoulli's theorem, and derivation of Bernoulli's theorem. Three things will be done now, and a figure to explain that. Yeah. So the application here, this application is for application for what? For equation of continuity. So that is why when you have pipes, yesterday I told you, when water is coming pipe, you make a smaller nozzle. When you make a smaller nozzle, what will happen? Area of cross section is reduced. When area of cross section is reduced, what has to increase? Velocity of the liquid has to increase. So an application of equation of continuity is only nozzle at the end of hose, not Bernoulli. Bernoulli will start after that. We're talking about Bernoulli's later. Okay. Now Bernoulli's theorem.
Now, actually, this theorem is true for any conservative field right now.
What?
Now, this theorem is true for any potential field right now.
Are you talking about Bernoulli?
Yes,
No,
madam.
not now. We start. Now, I just write down the equation. You'll understand the equation once I do. P by rho plus GH plus half V square is equal to P by rho plus GH plus half V square is equal to constant. Yeah. Now, what is Bernoulli's theorem? We have to understand that same tube you consider. That is, a tube is of varying cross section. If you take, what does Bernoulli's theorem say? Again, you have a clause. I told you that is why we learn what is streamlined. What are the clauses here? When an incompressible non-viscous fluid flows in a streamlined motion. These are three words we use for equation continuity also. When we started, we said consider a liquid which is incompressible, which is non-viscous, which flows in a streamlined motion, and then we started off the whole thing about what is equation of continuity. Same thing here, when an incompressible and non-viscous liquid flows in a streamlined motion from one place to another. One place to another means one part of the tube to another part of the tube. Then at every point on its path, the total energy per unit volume is a constant. So if you have a pipe like this, yeah, you take any point of the pipe, then you find that at every point, every point of this flow, if you calculate the energy per unit volume, energy of the liquid per unit volume, energy of fluid per unit, for 1 unit volume, how much is the energy of the liquid if you calculate? At every point you will get this value. What is the value? This you will understand after the derivation, so I am not talking about that now. P by rho plus GH plus half V square. What do you think would be P?
Pressure.
Pressure. Rho?
Density.
Density. G?
Acceleration.
Acceleration to gravity. H?
Height.
Height of the pipe from the ground. V?
Velocity.
Velocity of liquid is flowing in the tube. So what is the connection and how did you get this? We'll go later. So that is the main thing about Bernoulli's theorem. That's all Bernoulli's theorem is about. What is Bernoulli's theorem? When an incompressible and non-viscous fluid flows in a streamlined motion from one place to another in a pipe, then at every point on the path of that motion, at every point on the path, the total energy per unit volume is a constant. Total energy of liquid per unit volume is a constant, and this is the value. Now here, what was the conservation law and equation of continuity? Conservation. Which conservation happened here?
Volume and mass.
Mass conservation, remember I told you now. Total mass entering the tube is total mass of liquid leaving the tube. Here in Bernoulli's theorem, this energy conservation. Energy at every point is same. When I say it is energy, it will be on the board, so you will have an idea. So energy conservation is at every point with the flow of liquid, the energy per unit volume is conserved, or it's the same. So we have to understand first the whole thing. We'll understand the figure, then we'll start. It's a long derivation. Okay, so it's just 1, 2, 3, 4. 4 slides are there for that. So we'll start with the simple one, but first we'll understand it. Not about Bernoulli theorem, 2 minutes are because they get confused. I'll start. After I finish, you can ask it.
Yes.
So here, consider a tube. Actually, they are saying of variable cross section, but it looks like same cross section. So just imagine that it's a small variation is there in later cross section. This is a tube. The tube is not kept like this. Tube is like this. So it's like this. So one end of the tube is at a more height than the lower end of the tube. The tube is not horizontal. Tube is like this. Okay. So area of cross section. This area of cross section of the, so one end is called A and other end is called B. Okay. Area of cross section of the end A is A1. Area of cross section of the end B is A2. Okay. Next, height of the this area of cross section from the ground level is H1. Height of this B from the ground level is H2. P1 is the pressure of the liquid here, and P2 is the pressure of the liquid here. Okay. Then what about things? Yeah. Velocity of the liquid entering this is V1, and velocity of the liquid leaving this end is V2. Clear? What are the terms we define? Can you tell me? A1, B1, P1 and H1. A2, B2, P2 and H2. Any doubt what these 4 quantities are? Here what are the 4 quantities? Area of cross section A1, A2, velocity of liquid V1, V2, pressure P1, P2, height of the point A from the ground level is H1 and other one is H2. And the water liquid flows from A to B. So that is what we have to be. Okay, just read it.
Consider an incompressible non-viscous fluid flowing steadily through a pipe of variable cross-section. Consider 2 sections A and B as shown. A1, A2, the cross-sectional areas of A and B. B1, B2, the fluid velocities at A and B. P1, P2, the fluid pressures at A and B. H1, H2, the mean heights above the ground level at A and B respectively.
Clear as much? Yeah. Now, look at the previous slide. Okay. We need 2 quantities. One is force and one is stress. So here, pressure is P1 acting on an area of cross section A1. What is the definition of pressure?
Force by volume. Force by area.
Correct? So what is the force acting on this area of cross section?
F1 A1.
P1?
P1 A1.
we'll keep the pressure force as pressure into area of cross section. Now, distance travel. Suppose you take a small distance from A to A dash. Okay, the body, the liquid has traveled from A to A dash in a time t with a velocity v. Then what is the distance travel for the small interval? What is the distance travel? Velocity into time. So we'll see that. Yeah, we call it by delta t. Sorry, not delta t. We take it as delta t. So here force is P1 A1 and distance travel is V1 into a time interval delta t. In a time interval delta t, how much is the distance traveled by the liquid? It's velocity of the liquid into the time. So force and distance you get. So what is the work done equal to?
E1, A1, V1 delta.
Yeah. What is work definition in terms of force and distance?
Force
and distance. So force is P1 A1, distance is V1 delta t. So what is the work? P1 A1 V1 delta. Yeah. That's all you're going to do. Next slide we'll see that. So we are here. Here I think we read. Okay. Now what is P1 A1? P1 A1 is the force acting on the liquid layer at A. Correct, that you understood? Is it small p or capital P?
No, capital.
This capital P. So please see that the same capital P you learned it here. It's capital P, P1 A1. Now under this force, at a time delta t, the layer will move through a distance I told you. What is the distance traveled? Velocity into time. Now work done on the fluid. Now what you understand one factor here is, here work is, here work is done on the liquid to push the liquid to the tube. Here work is done by the liquid to move from B to B dash against this pressure P2. So here work is done by the liquid here, and here to reach to enter the tube, work is done on the liquid. Now what is work equal to? Force into distance. Correct? Force is equal to P1 A1 and distance is equal to V1 delta. What is the work done here?
Work done.
What is work done equal to?
A2, V2 by A2, V2, V2.
Same delta. Okay. So when you need to do work on the liquid to push the liquid from A to A dash, here the liquid has to do work to go from B to B dash, from B dash to B against the pressure. So there is work done on the liquid and work done by the liquid. On the liquid is P1 A1 V1 delta T. By the liquid is P2 A2 V2 delta T. Clear as much? So work done on the liquid. That's what we saw just now. Work done on the fluid is P1 A1 V1 delta T. Okay. Now work has to be done. That is what the liquid has to do work to go from B dash to B. And what is that work equal to? That work is equal to P2 A2 V2. Have you understood this too? That only maths. Just once we go to the picture here. The force acting on area of cross section here is P1 A1. And the time taken to travel from A to A dash is delta T. So distance traveled is V1 delta T. So work done on the fluid is A1, P1, A1, V1 delta T. Here work done by the fluid is P2, A2, V2 delta T. Clear? That's what we see till here we have done. So what is the net work done on the fluid? What is the net work done on the fluid? One is there, one work is done here and another work is also done. So combined together. So what is the net work done on the fluid? It is work done on the fluid at the entry point minus the work done by the fluid at the exit point. Okay. So this is what we saw just now. Till here is clear? Is it clear till here? Then only we will go forward. After this is just rearranging the basic thing, understanding part is clear. Okay. So it's simple. Looks complicated because so many equations and figures and all that. It's not. Okay. Now we'll start this one. Rearranging. So here now equation of continuity. What was equation of continuity? A1 V1 is equal to A2 V2. If you add a delta T on both sides, will the equation change? Delta T, if I multiply, will the equation change? No. So they are writing A1 V1 is equal to A2 V2 we know from equation of continuity. Add a delta T. So A1 V1 delta T is equal to A2 V2 delta T. Correct? Now what is A1 V1 delta T? What is A1 V1? Volume by time. So if I multiply a time into this, what you will get? Volume. Clear? A1 V1 is volume by time. So A1 V1 into delta T or T, it's a time, is V by T into time. What is V by T into time? Volume. So what is this A1 V1 delta T now? It's a volume. And what is A2 V2 delta T? It's also a volume. Are the two volumes same or different? Same. The volume entry has to be equal to same, which has given. So here you understand, we are writing what? A1 V1 delta T is equal to A2 V2 delta T. A1 V1 delta T can be called as V. A2 V2 delta T also can be called as V. Okay. Now V is volume. Volume is equal to mass by density. Volume can be written as mass of liquid by density of the liquid. Now we come back to this equation. Now in this equation we go P1. Let's show here. This we come to this equation. P1 into A1 V1 delta T minus P2 into is it correct what I have written now? P1 A into bracket you put up. This whole thing is V, this whole thing is also V. So P1 V minus P2 V. Yes. Is it correct? P1 minus P2. That is why we wrote this equation as P1 minus P2 into V. Now V, what is V? Just now we wrote, what is V equal to? M by rho. So instead of V you write M by. Just rearranging children. That's why you have to today go home, open this whole thing and just take a pen or pencil and 1 hour you need to just see. Whether don't by heart or anything or learn anything. Whether you know how one step to other step is coming. It's just rearranging, it's just nothing else, okay? So here this whole thing is V, then you get this, V is M by. So we got a final equation, total work done. So net work done on the fluid is work done on the fluid minus work done by the fluid. And what is the net work done on the fluid we got? We got P1 minus P2 into M by. That is the work done on the fluid for the liquid to move from one end of the tube to the other end of the tube. Now, this is the thing you need to know. Work done increases the energy of the fluid. The work done on the liquid will increase the energy of the fluid. What are the two kinds of energies that you know? Potential energy and kinetic energy. What is the equation for potential energy? mgh. And what is the equation for kinetic energy? Half mc. So what do you think will be the potential energy here? mgh1. What will be the potential energy here? mgh2. What will be the kinetic energy here? Is there m1 v1? m1 both are m because same. So what is it here? Half m v1 square. What is kinetic energy? Half m v2 square. So we'll see that. So we have derived and kept one part saying the work done on the fluid is P1 minus P2 into M by rho. And now we are saying work done will increase the energy of the fluid, and we'll go to the next step. So here, don't go for this part. I think from here you can start and understand it better. Work done on the fluid, I calculated and kept this from the previous slide. That is equal to, I told it increases the energy of the liquid. What are the two parts of energy? Equal potential energy and kinetic energy. So this has to be equal to increase in potential energy plus increase in kinetic. So what is the potential energy? Increase in potential energy is potential energy at one end minus the potential energy at other end, which is this. And what is increase in kinetic energy? Kinetic energy at one end minus the kinetic energy at another end, which is this. So this two you take it and substitute it. Now we go to the next simplification. So till here, is it clear to all of you how we got this? Work done on the fluid is equal to increase in potential energy plus increase in kinetic energy. Now we simplify. M, and the liquid. So what do you get? P1 by rho minus P2 by rho is GH2 minus GH1 plus half E2 square minus half E1 square. M is 1. Now here rearrange. So I'll show you. P1 by rho I take from here. This minus GH1 when it comes to the side, what will become? And if minus half E1 square comes to this side, what will become? What take? Minus P2 by rho when it goes that side, by rho is coming. GH2 is already here, half of this. So what have you done? All the 1 terms on one side and the 2 terms on the other side, and you have rearranged. Is this the first equation that you saw?
Yes.
Yeah. Now what is this? This is the total energy per unit volume at point A of the tube, at the starting point of the tube. This is the energy per unit volume at the end of the tube. Are they same or are they different? They are same. So energy is constant over the flow of the tube. At one end of the tube and the other end of the tube. So P by rho plus GH. See there I put P by rho plus G. So all the 1 and 2 suffix if I remove, what is left out? P by rho plus GH plus half V square is a constant. P by rho plus GH plus half V square is a constant. Clear so much? Yeah. So what is this? This is what we are seeing this now. P by rho plus GH plus half V square is a constant. Now divide the whole equation by G. What do you get to divide the whole? So from, I think you can like, if I ask for an exam, derive an expression or prove Bernoulli's theorem, this is enough to stop. Here you can stop. This whole thing is extra. You need not mention. You'll get the full marks if you finish here. Now these are little extra things about that equation that we're talking about. So here you divide the equation by G. So here one G will come, here one G will come, here one G will come. This G and this G will cancel. So you get P by rho G plus H plus half V square by G and also is a constant. Now this is called the pressure head, this is called the gravitational head, and this is called the velocity head. Gravitational head, pressure head and velocity head. So these are the 3 things which are constant. Now we take a special case. Now the case that we are seeing now is this, if you remember, something like this. Okay. Isn't this the case that we are seeing? Liquid is going like that. Now suppose instead of this you take a horizontal tube. What will be H1 and H2? Same. H1 and H2 are same. So if you take out H out of the equation, if H is same, you take out H from the equation because right hand side and left hand side H are same. You cancel the 2. What is left out? What is the equation that left out?
P by rho G plus 1 by 2 V square by 2.
So along the tube, at any point of the tube, this has to be a constant. If you take a horizontal pipe, not like this, any horizontal pipe, along the tube anywhere, any point you take, this should be a constant. In this, what is rho? Density of liquid. No problem, it's a constant. What is G? Again, it's a constant. So what are the 2 variables here? Pressure and velocity. Somewhere in the tube, if pressure increases, what has to happen at that point? What should be there to make it constant? Velocity. Somewhere in the tube, suddenly pressure drops. At that point, to make this constant, what has to increase? Velocity. So that is the main thing about Bernoulli's theorem. So Bernoulli's theorem just says, now this is from equation of continuity. Wherever area of cross section is more, velocity is less. So what does Bernoulli theorem say? Wherever pressure is more, what happened? So A is more, area of cross section more, what happened to velocity? And if velocity is less,
Pressure.
you combine this and this. And this is a lot of application questions, entrance levels, in our normal exams, everything will come. That if you have a tube of 2 different cross sections, bigger and smaller. Smaller cross section, velocity will become what? More. Just now you learned. Lesser cross section, the fast it will go. Velocity is more. Velocity is more at a point in a tube means what has to happen to the pressure? Velocity is more means pressure has to decrease, and that is because this I showed you now. This plus this has to be constant over all the length of the tube, over all the flow of the tube. And if you remove it up, even if you take this kind of tube, then H1, H2, another factor is also coming. If you take a horizontal tube, then H factor goes away, the second factor goes away, so this plus this is a constant. P increases, P has to reduce. Any doubt here? Yeah, that's about what is Bernoulli's theorem. Okay. Go through that, all this. Now, this is what I have written now. A more, B less, P more. That same thing in terms of statement. Yeah.
clear from the equation of Bernoulli's theorem that in a flowing liquid, where the velocity of flow is less, the pressure is larger and vice versa. If a liquid is allowed to flow in a tube which is narrow in the middle, then in this part the velocity of the liquid is greatest and the pressure is smallest.
Alright? This is the relation. So if A is less, what will happen? The velocity is more. Velocity is more means this theory of velocity less pressure more pressure less is used in all the applications of what are the different things you'll see. Applications of Bernoulli's theorem basically uses this theory. Velocity less pressure more pressure less. Okay, that's all. So what are the assumptions? You saw a lot of assumptions are made for Bernoulli's theorem. Non-viscous, incompressible, streamlined, irrotational, no rotational motion or anything like that. Okay, no loss of energy. And sometimes all of this is not true, so corrections have to be applied. We are not going to study any corrections or any complicated part of this Bernoulli's theorem. But you have to understand, suppose suddenly you take a liquid of viscous liquid, then Bernoulli's theorem, some correction has to be applied. Or we take something which is not streamlined, then Bernoulli's theorem correction. So we are not going to the details of corrections of Bernoulli's theorem based on the assumptions not being followed or anything. But I can ask you give 3 assumptions made in Bernoulli's theorem. So you just learn at least 3, 4 and 3 from this set. Yeah? All these are these 3 are at least this 3 if you don't know. At least the first 3 you are aware. Non-viscous, incompressible and streamlined. Now what are the different applications of Bernoulli's theorem? Now I told you the main application is only this. Okay? Based on this only, everywhere you see this will be applied. Some place where velocity becomes, this whole thing you can say. When area of cross section is more, velocity less, pressure more. Area of cross section less, velocity more, pressure less. Okay. So we'll see the first one is called an atomic. Now this is again, what I have done is, when I sent the PPT, yesterday when I was going through the PPT, I tried to remove all this. Okay. I hope in the slide that you see will not be there. These are all a part of some other picture. So there's nothing about this in this. Okay. I tried to put a box and then color the box with white that I've done yesterday and sent. I don't know when it comes in Google Classroom whether it will come up again like all this. Okay. So this is put here before that. So check on that if anything is there. So here it's very simple. It's called atomizer or spray gun. So it's like all the perfume tubes and spray, anything where you press it and a fine beam or fine spray of liquid comes out that has an application of Bernoulli's theorem. So what is the application? You have a jar in which some liquid is filled. There is a tube attached here. This tube is going to another tube and you have a small rubber balloon or something which you can press here. Air will be there. So what happens when you press the air here? When you press the air here, what happens? The air will start flowing with a large velocity. Correct? So the air, normal velocity, the air would have gone in one velocity, but because of the pressure that you're pressing that you do, large velocity air will go here. So at this point, velocity is more. At this point, correct? Because air is coming in. When velocity is more, what happens to pressure? Less. P will be less. So pressure here is lesser than pressure here. So what happens to the liquid? Liquid will rise up. Liquid will rise up. When liquid will rise up, liquid reaches here. This liquid will mix up with this air and go out as fine spray. That's all is the atomizer. Clear? That's what I'm telling you. You press the air. When you press the air will travel here with large velocity. Velocity becomes more. In this tube, when velocity becomes more, pressure becomes less because of Bernoulli's theorem. When pressure is less, the pressure here in the external tube is lesser than the pressure in the internal jar. So the liquid will rise up and reach here. And when the liquid reaches here, a small quantity of liquid when it reaches it, it mixes up with this air, and with that velocity goes out and goes as fine spray outside. So that's all what is
Now, how is there always air in that round?
See, that is what. See, when you, it may be like a hollow thing where you can press in. See, every time you see anything you press, that's just goes and comes back. So maybe it's a air kept like that. You can detail, you can see how it is working out.
It's like that. Actually, also the symptoms for when you evacuate the air chamber, it's open at the end. And when it's released again, the pressure inside the air chamber or rubber balloon is less. So air from outside will come and fill up again.
Air from outside?
Yes, and since it's open at the end, right? The nostril is always open.
You mean from here?
Yes, ma'am.
So you're saying air is coming in?
Yes, and once we release the rubber balloon, since there's pressure, since it's evacuated at that point, then
you're saying air will anyway come from the other side, but you can see the difference. So here,
this thing is like similar thing is used in carburetors.
carburetor for that spraying, maybe, you know, but they're pressing it on with this.
No, it uses air which is being forced over the.
It will come back like that, maybe. So here, you can, this whole thing is what I've explained now, you can read through, okay, we're not going to. Now next is something called venturi meter. Now venturi meter is a tube XY. So you have a tube XY which is of one cross section, but here at one point the cross section is less. So you can see the tube. See here, basically the tube is like this. It has everywhere a cross sectional area A1, except what happens here, it has dipped. So what is the area of cross section here? It is A2. So tube is X5, area of cross section A1 is of the tube, but at one point the area of cross section is small, which is A2. At the area of cross section where it is A1, you have kept a tube which is rising up, the liquid can rise up here. And at the area of cross section A2 also, you have kept a long tube, the liquid can rise up here. So this is the Z point. Okay. Now what we find here is, this is A1 velocity V1, A2 velocity V2. Now what can you say about A1 and A2, which is greater?
A1.
So what can you say about V1 and V2? Correct? A1 is greater than A2, so V1 is less than V2. When V1 is less than V2, V2 is now greater. Then V is more means what happened to pressure?
V1 is greater.
Pressure here is more than pressure here. Here pressure is less, so the rise in liquid is also less. Here pressure is more, so rise in liquid is also more. So what happens is the difference in these two levels is taken as H. The difference in level. So basically this whole thing is coming as a combination of, it's actually not only Bernoulli's theorem, because A1 V1 equal to A2 V2 is a constant. Is it from Bernoulli's theorem? No, it's from what? Equation of continuity it is. Okay. So A1 is greater than A2, V1 is less than V2, P1 is greater than V2. Pressure here is lesser than pressure here. So the rise of liquid in this tube is lesser than this tube, and basically from this whole setup, the experimental thing, that data that we need is, what is the data we calculate is only H we need. Okay, what is H? H is the difference in height from this tube and the other tube. This difference in height H is because the area of cross section A1 and A2 are different. Now we'll go to what this whole thing does and how to be applied. Is it clear, the figure and the explanation? So we'll go for this. Venturi meter is a device based on Bernoulli's. Venturi meter is a device which is based on Bernoulli's theorem. Okay. It consists of tube XY. I told you the whole tube is XY. In center, the Z alone you made it very narrow. It is joined by two vertical tubes. At one bigger point you put a vertical tube. At that constriction, small cross section also you put a two vertical tube X and Z. Now this is connected with a tube in which rate of flow of water can be calculated. So what does a venturi meter do? Venturi meter calculates the how much water is flowing, rate at which water is flowing in a tube can be calculated just by doing this full adjustment and finding out that H. The whole adjustment that we saw, plus that only the measurement that you have, the data that you take from that is small H value. Knowing just the H value, you can calculate the rate of flow of water. Now when water flows in this whole thing we saw, when water flows in the tube, velocity is larger, hence the pressure is less. This pressure difference is measured. From this the rate of flow of water can be calculated. So basically whatever I told you now just before is the same thing. You have one big cross section, one small cross section. Bigger cross section, rise of water is more, lesser is smaller. Difference in height H. If you calculate H, you can find out rate of water flow or rate of flow of water in the tube. Now this rate of flow of water equation we are not deriving. It's first thing to understand. Okay. So the rate of flow of water Q is what is the rate of flow of water? It is equal to A1 A2 root of 2GH by A1 square minus A2 square. So we are not deriving this, it's not coming to any of the previous equation, we are just writing the equation. Okay? Because meter is just a part of Bernoulli's theorem application. We are not going to the detail of that. Do we understand what these quantities are? Yeah, what is Q? Rate of flow of water means what? Volume of water flowing per second. So what is Q? Volume of water flowing per unit time. What is volume of water flowing per unit time equal to? Look here. What is the volume of water flowing per unit time equal to? A1 V1. That is why we have written here as equal to A1 V1. That volume of liquid flowing per unit time A1 V1 of Q can be got as this big equation. That's what you understand. Okay. Now this big equation, let us see whether we understand it. What is A1 and A2?
Area of the X answer.
Area of the bigger one and area of the small construction. G. Acceleration due to gravity. H. So what is the only thing that you are noting down from the device? H. H also you are noting down. A1, A2 also. A1, A2, H if I know, I can actually calculate how much water is flowing in the tube per second by doing this equation. That's all what we have written here. Okay.
Ma'am, so that capital A1, capital A2 root of we just have to know it.
Sure.
The third part of the equation we just have to know it.
Which one? This one?
Yeah.
No, we are not deriving.
Yeah, so it's just an equation that we have to learn.
It's just an equation we are learning. See, I cannot tell you from here how I got this. Is there any connection? I can't tell you. I'm not taught you anything about it. So you just understand that Q is volume by time. Volume by time you have already, this part you know, this much you know. And that can be written, and this you have to by heart. A1 A2 root of 2GH by A1 square minus A2.
We have to do diagrams and then the equation.
No. Which diagram? The tube. That depends on how it is asked. Okay. So you mean I will be asking, explain venturimeter means figure has to be. You put the figure, give a small explanation of the figure in your own words, and write the final equation. Next is very simple. It's a big explanation written on the board. So you can go through that, learn this in your own words and write for exam. Okay. So we're not going to go to the explanation. It's a very simple theory. It's called Magnus effect. Spin of the ball. So tennis goes to play. Okay, tennis cricketers all are here. So what is that called? Cricket? Swing, no?
Oh.
Swing or whatever. So what happens is, suppose you take a tennis ball or a cricket ball and you throw straight. The ball will go like this. Okay, it will not go turn and all. It will not go. When I go, the batsman can predict how the ball will come and it will along with that. But when you spin, what will happen? You have this outswing and something.
Outswing and swing.
Outswing and swing and all is there. No, something and all is there. So the batsman cannot predict because it will go in different direction. Okay, and the ball will go in a complete curved path. Basically, the ball will not go in a straight line. If you spin the ball will go in a curved path. Okay. Now that comes from Bernoulli's theorem. I'll tell you how. So here what happens here is, again I'm not going to read out the explanation for you. So you can go through this later. So if you take a ball and you put straight, you're throwing a ball. You're not spinning it, you're just throwing it straight. What happens here is, there is velocity of air coming backward. So when the ball takes the place of the next position, something like this you throw, velocity of air up and down of the ball is towards this side. Velocity is this side and the ball is going like that. That's all. V1 is air going this side and the ball will go off straight like that. But suppose along with throwing like this, I twist the ball or spin the ball and throw. There is initially, this is already there, this here. But along with that, I have done a spin to the ball. So there is a U spin of the ball this way and a U spin like this. Correct? You have to spin the ball. So top part there is a spin to this direction and down part there is a spin to of this direction. So what is the net velocity at the top? Are the two velocities in the same direction or different direction? What is the net velocity at the top?
V1.
What is the net velocity top? But in this case, if a ball is going straight, what is the velocity at the top and down? V. Now it's not V and V, it's V minus U and V plus U. Which velocity is less, which velocity is more?
V minus U is less.
V is less. And the V is... When V is less, what will happen to pressure? P is more here at the top, P is less on the top. And because of the pressure difference, the ball will go in a curve.
I thought you usually a backspin, right, man?
Huh?
It will usually be a backspin. It will start going this way.
How will you go backspin?
Ma'am, because the pressure difference is more on top and bottom. And sort of net force will be directed this way.
So you are saying it will go like this?
Yes, ma'am.
It will go like this?
Yes, ma'am. It will go like this and it will
Yeah.
curve like this.
Yeah. It will go in the curved path. Basically, it will not go straight like that. Okay. So that will help the the bowler or the player. The other person cannot predict where it will go, and that is the reason they do the spin. So we'll just read through this thing. This is the only theory you need. Okay. Now for venturimeter, atomizer, and Magnus effect, figure is very, very important. So if I ask you to explain Magnus effect or explain venturimeter, I would expect you to draw the figure. Explanation of the figure and all the things can be done in your own words. Okay, no, there's nothing about same words to you. The basic theory is you have to show how velocity less, pressure more. Velocity more, pressure less. All that things should come from the explanation that you write. Okay, or people write on the figure also. See here, not the figure is if I wrote V minus U, pressure more, V less. V plus U, V. This like this you can make your own figure. A little extra data you can. Let us read this. Yeah, Smitha.
Magnus effect. Tennis and cricket players usually experience that when a ball is thrown spinning, it moves along a curved path in the air. This is called the swing of the ball and can be understood by figure 18. When a ball moves forward, the air ahead the ball rushes with velocity v, say to fill up the space behind the ball, which has been left evacuated by the ball. When the ball spins, the layer of the air around it also moves with the ball, saying with velocity u. Thus, as is clear from the figure, the resultant velocity of air above the ball becomes v minus u, and that below the ball becomes v plus u. This means that the velocity of air above the ball is reduced and that below the ball is increased. Hence, according to Bernoulli's theorem, the pressure above the ball increases and that below the ball decreases. This pressure difference exerts a force on the ball due to which it moves along a curved path as shown. This effect is known as Magnus effect.
This is a pretty long explanation. If you want, instead of so much explanation in terms of like, we can say, take a ball, the top part of the ball, the net velocity is v minus u. Therefore, it's less velocity. So it's less velocity, therefore pressure is more according to Bernoulli's theorem. Like that you show for the bottom part. Then you say, since because of this pressure difference, the last line is good. This pressure difference exerts the force on the ball due to which it goes in a curved path. This is known as. So you need not write the whole thing, but you should be putting that v minus u and p and v relation. Basically, this relation should come into the explanation. Next is dynamic uplift. You have this. Anyone is doing an aerodynamics now? Jabez. So aerodynamics and why there is something like uplift, there's some force which is pushing the body upward, or maybe like when you make like a plane thing also, when you make this paper planes and you then, or anything, this shape is called an aerofoil shape. So the down part is little flat and the up part is little curved, like wings of a plane. Okay. Now what is the use for that wings of the plane, the top part being curved and down part straight is? Again, we are using the Bernoulli's theorem for that initial actual lift of the body in the air. See, there is fuel, everything is there, but there is something called an uplift or upthrust of the body towards up. So that lift of the airplane is coming dynamic. It's called dynamic uplift, and this uplift is again based on Bernoulli's theorem. And Bernoulli's theorem is only this. Or somewhere you are making velocity less. If you make velocity less, pressure will become more. If you make velocity more, pressure will become less. Okay. So we'll just see that. So what is meant by aerofoil? Okay, this is an aerofoil. Aerofoil is a solid piece. It is a shape which is known as the aerofoil shape. Okay, basically you're talking about the shape. So aerofoil is a solid piece properly shaped so that the upward vertical force acts on it when it moves horizontally. Airplanes get lift because of this principle. So basically you have the shape like that, and which gives an initial uplift for that body, goes upward like that. Okay? And so here what we do is, suppose you had something like this shape. Okay, so what will happen? The velocity of air will go like this. Same thing like a ball going straight. Just now we showed, no? Ball thrown like that. So when something is going, something is shaped like this, the air around it will go straight like that. velocity, same velocity everywhere. So there's no pressure difference, no velocity difference. The air will go like that, body will be like that. Now because of the shape, so what we have done is we made one side curve and other side is flat, like this option. Wings of an aeroplane are shaped. Now what happens is because of the curve and the air goes like this, it goes faster. Because of the curve, the air goes faster at the top. And here, so velocity V1 is more at the top because of the shape. Here velocity V2 is less. So if V1 is more, what can you say about the pressure? Less. And pressure will be less at the top and pressure will be more at the bottom. So here V1 is greater than V2. So P1 is less than. Now pressure is less, pressure is more. So what will happen? It will lift. It will lift. And because of the pressure difference, there is an upward lift of this aerofoil. So the upper surface, we'll ask someone to read through here. This is an extra line. So like this extra lines are there, so then you just have to cut it out. Okay? It's part of pictures have been taken from textbooks and all that. So here. So this is what. So basically you have to tell in every explanation that you do how velocity is more. When velocity is more, what happens to pressure? And because of the pressure difference, this is happening. Writing everything and not even telling about what is V1, V1, V2, V2 and why it is uplifting, you give a big explanation, you will not get marked. These are all keywords that you have to explain for. Yeah? Yeah. Sasha, read.
The upper surface of the aerofoil is more curved than the lower one. So the fluid flows faster over the top surface than at the bottom. Streamlines are closer above because of the higher velocity. Thus, the pressure above becomes less than that below the foil. This pressure difference gives rise to an upward lift called dynamic lift for the aircraft.
Simple, no? It looks very good. See, big explanation, but big figure, no, nothing is there. Like everything we are trying to say that some reason velocity becomes less and more. That's why pressure is becoming less and more. Bernoulli's theorem, just Bernoulli's theorem, this equation and all is not coming in any application. What is Bernoulli's theorem coming? Only this. From this only, this we got. This is only what we got as Bernoulli's theorem applications and come everywhere. Any doubt here? Yeah?
Ma'am, so like the air below, why is it going curved? Why is it like not straight?
No. It's not. It's actually like this. That is it will show like that. It will draw like this. It will not go like this and like that and all. It's already there in the picture textbook, so I just went. So basically, you can show the top one, you can curve it. Down one is like this. Next is something called Poiseuille's formula. Again, this Poiseuille's formula we are not deriving. We are just writing, and then we are understanding what are the terms. So there are certain things where we don't have to go to the details, but it's there in the syllabus, so we go through that. What does Poiseuille's formula say? Again, it is the volume of water flowing per second. So we have to come back to something. What is Q here? Volume of liquid flowing per second. What is A1, V1? Volume of liquid flowing per second. What is this whole thing? Volume of liquid flowing per second. Same thing. Volume of liquid flowing per second is also got by another new equation. That's all. So rate of discharge and all, don't worry about the words. What is rate of discharge? I have to mention it. Volume of liquid flowing per second. From the beginning we have been talking about how much is the volume of liquid entering the tube. How much is the volume of liquid leaving the tube? Volume of liquid per second of the tube is what is known as 3 different equations. So that the early equations also for volume of liquid, that will come under which category? Venturi meters application. Bernoulli theorem application, Venturi meter. This is volume of liquid per second, another equation which comes under Poiseuille's formula. Then this formula is called Poiseuille's formula. Okay. So what is it? It is just equal to Kpr raised to 4 by eta L. And K is a constant which is equal to pi by 8. Okay. Now what are the terms you learn, and that's all. So this equation is called Poiseuille's relation, and from this basically you understand Q is equal to pi P r raised to 4 by 8 eta L. What is eta? Can you tell? Coefficient of viscosity. And next section is viscosity. You'll understand what it is. Eta. So can I calculate eta from this? What will be eta equal to?
Eta will be equal to Q 8 by pi PR.
So Poiseuille's equation can be used to find the volume of liquid per second. or if you rearrange, you can even find the coefficient of viscosity. So we need to know what these terms are. Okay, we'll go to the next one. Now eta is the eta is the coefficient of viscosity. K is a constant. This is volume per second. What are the three terms we need to know now? P, R, and L. Other terms are clear? Q is volume of liquid entering the tube per second. Eta is coefficient of viscosity. It's a constant based on how viscous your liquid is. K is a constant equal to pi by. Now P, R,
P is pressure.
so P is pressure. Capital P is small P. Yeah. So if you write capital P also no problem. It's there, it's written small. So P is pressure. Okay. And L is length of the tube and R is the radius of the tube. So if you have a tube like this is radius, this is length, P is the pressure of the tube, and the liquid's coefficient viscosity is theta. So P by L, pressure per unit length is a new name. What is pressure per unit length? P by L called pressure gradient. Pressure per unit length is also called pressure gradient, P by L. If you don't want to learn pressure per gradient, directly learn it as P the pressure, R the radius, L the length, and eta the coefficient of viscosity. So I'll ask you, give the equation, give the Poisson's formula and define the terms. That's all I can ask you. I can't ask you anything else. Give the Poisson's. Now, in this exam, I told you in all the exams till your 11th standard finishes. Okay? If I ask you what is the relation or give the equation, I mean only the equation. This has to be given. No need of derivation. If I need derivation and ask you derive an expression, explain the equation. So derive and explanation are two terms. You need to make the explanation. If I say what is it, give the relation, or only write the equation and define the terms. So that's all about this. So that's our properties of bulk matter, the third PPT. The fourth one we talk about, till now we have been talking about viscosity, correct? So what is viscosity is your next one. The whole thing about, the whole slide, the whole PPT is about viscosity. Has Geeta ma'am taught you viscosity? Is she teaching? She said something, she will leave at that. I told her viscosity and surface tension and everything. I think thermodynamics yesterday.
She said she told you the nature of gases and stuff.
What is it?
The movement of gases.
Even for me, when I do heat and thermodynamics, so many things, even kinetic theory. Kinetic theory, heat and thermodynamics fully is that Boyle's law, Charles' law. Have you studied?
Yes, ma'am.
Boyle's law, Charles' law. Then many things which are understood. Many things of chemistry. Basically a chemistry section. But heat and thermodynamics in physics and chemistry are little different. In sign convention is different for both. The sign convention is opposite in chemistry and physics. Okay? And the explanation, this will be more of the physics part of it. And chemistry ma'am will be doing more of chemistry. I think she's starting after this now, heat and thermodynamics. What is she teaching now?
Organic.
Now she's teaching. She told after vacation, she said, for me I'll start only after this. Maybe 1 more week or 2 more weeks. After this we will go to thermodynamics.
Physics is more of a statistical interpretation right now.
Yeah?
Now in physics, thermodynamics and kinematics of gases, it's more of a statistical interpretation right now.
More of what?
A statistical interpretation.
Statistical.
Yes.
Correct. There will be more of that chemical thing about it.
Yeah.
Here we won't be doing it. Just take a 2-minute break. Then we will start. Anyone got project to check or anything?
I have some questions about it.
What?
I have some questions.
Okay.
Is this some format stuff? I mean,
Just take a 5-minute break, then we continue. You brought your project? Then come ask. Now you ask, because after 10:30 I will sleep. What you did? What is that? I don't see it's recording. Martha's doubts. Okay, yeah.
We should get that right. We are discussing the point.
Understood. Index is a ball. You don't want to put a border for that. not is your choice.
Able to keep from thinking. Can I put it less?
Select a picture. That's the second one. Any doubt in project you can ask because you have submission 13. If you enroll 50, when are you submitting your project? Submitting. You finished?
I'm just a lab writer.
Oh my god, you see
Then
she
Monica,
zoomed
you
in.
finished your project?
Almost.
Huh? Almost. When did you go?
On Friday.
Oh, you didn't know you were there for vacation.
I was there for the beginning of our picture.
Beginning of?
But supposed to only speak on the left side.
Friday is this Friday. So you were there? No, that's a week you were there.
Oh, sorry, I thought I asked you to pick it up. Sorry. I don't want to worry.
There's lots to this. Like,
And then go to the other.
okay, when you listen, then you will later
No,
take this out and start
I'm going
studying.
to put first the content page and then take the same page, put it the other way around.
Leave space in the insert page. In a second.
That's why I'm on the back side.
Because you want to spiral back.
No,
Otherwise you will try.
I didn't do double sided because my printer will take more, it will take up more toner and all. And then I can't waste it.
Last thing is started.
This is here.
I checked yesterday.
Enough. It's enough.
This is the school band.
That's okay. Nothing will happen. That's not any more of it. Something happens. Ask them to the project is not going anywhere out, so you don't have to worry too much about the project. Because the project, next year they will check the 12th project, not the 11th. This is your rough draft of 12th project.
Ma'am, that's why I was saying let's just stick it.
No. But the format, I am giving marks for the format. So when I cut for someone, I can't give you mark for that. So if I have told you a particular order where the certificate should be, where the content should be, and you mismatch and you put something like you want, I cut marks for that. I'm not going to give back the project. I just take all the project in one page. I will write what are the mistakes that you have done, keep it in the project, and I'll give the mark accordingly. That's all. I won't give back the project at all. I won't even tell you what are the corrections. No. Same project, I take it out in 12th standard when you are, and then I'll tell you from the beginning what are the things that has to be changed and all that. So try to follow what are the answers. So if you have any doubt, we have one more day tomorrow. You can even bring your project in this one and show, or if you have any doubt. That's what I told you. So let us see the next one. So we have been talking about viscosity from some time now. Viscosity is like that, coefficient of viscosity is like this and all that. So what is actually, this is another section which is very important. Yeah. So this is another section which is very important and very simple also. Viscosity and what is coefficient of viscosity and all that. Now here what you can understand is, let us go to what is friction. We learn what is friction, we will do an exam on that. So friction is, basic definition of friction is what? If you have space, you have a body which is moving like this. Okay. You have a body which is a body is moving like this. Then what will be the direction of friction? And tangential. You have a tangential force which is acting, which is opposing the motion of A on this block. So the A, when I try to move on the surface, there is a tangential force opposite which is trying to oppose this movement. That is known as friction for solids. The same thing is happening in liquids. So inside the liquid there are different layers of the liquid. Okay. So when the layers move, there is one layer and the other layer moves. There is between them, what is there? There is an internal friction of the liquid, and that internal friction of the liquid is trying to oppose the movement of one layer of the other layer. And that tangential friction inside the liquid is given the name viscosity. That's one way of telling what is viscosity. We'll see all the other definitions of viscosity also. So what is viscosity? We start with the same thing that I told you. When this is not viscosity, this is basically solid. A solid body slides, a frictional force begins to act. This force opposes the relative motion. This is friction. Now we'll come to our thing. Similarly, so we're talking about why, because you already know what is friction, so you can connect to that and think. This is friction inside the liquid. What is it? When a layer of liquid slides over another layer of the same liquid, there is again a frictional force acting which opposes the relative motion between the layers. This force is called internal frictional force. And that internal frictional force is nothing but due to the property of viscosity. So one layer of liquid and the other layer, when they move, they have an internal friction between the layers of the liquid, and that is one way of telling what is viscosity. So if I ask you define viscosity, you don't have to tell me any of these. Okay? This whole thing is for you to understand what is viscosity. So if I say define viscosity, I need this. What is viscosity? The property of the liquid by virtue of which it opposes the relative motion between its adjacent layers is known as viscosity. The property of a liquid by virtue of which the one layer of the liquid, other liquid layer, they oppose the relative motion between the adjacent layers. You're not going to have this layer and the 10th layer. This and the next layer, this and the next layer. So two layers are moving. So when the two layers move, because of the relative motion, there is a property which is known as viscosity. When for liquids which are more viscous, like honey, oil and all, when liquids are more viscous, what can you say about this internal frictional forces? More. That's why the fluid is not flowing easily. Is it flowing easily? We take honey and then pour like that. The liquid is taking them some time to come down. Why? Because of that internal frictional force. But as you take water and pour, water will just flow off like that because there is no internal frictional force inside the liquid. Water is less. Now these are the different layers. You have to understand, it's like suppose you have here and water is flowing into this different layers. So this is the topmost part of the water, like water in a river, and this is the down. And this is the surface. Now you have to understand the layer which is closest to the surface has zero velocity. The layer which is right at the bottom touching the surface down is having zero velocity, and the layer which is right at the top has maximum. You should not imagine that the whole liquid is flowing with the same velocity. No. The top downmost layer is of zero velocity and increasing velocity, and topmost will be flowing with maximum velocity. That's one thing that you have to understand. Is it clear, this slide? Now this whole thing is again, I'm talking about viscosity in different ways, again explaining. So this you have to understand, the key is only this. So learn only this by heart. Okay, this and this you can just understand what is viscosity. What is viscosity? The property due to which a liquid opposes the relative motion between the different layers, and the tangential force that tends to destroy the relative motion is called viscous force. Viscosity is the internal fluid friction. Viscosity is nothing but internal fluid friction. And the tangential, I told you it will oppose, no? The tangential force that is opposing the movement of the two layers, that force has a particular name. It's called viscous force. So property is viscosity, force is viscous force. The property of a liquid to oppose the motion of one layer and the other layer is viscosity, and the force that is doing this opposition is called viscous force. Now these are all the examples of viscosity seen from daily life. So this no need to use the same words, you read through and in your own words you can learn. So basically you are talking about why certain things will flow slowly, why certain things just flow off quickly. So what you have to understand is inside the liquid, more the friction, more the viscous force, the liquid will not flow easily. Inside the liquid, less frictional force or less viscosity, less viscous force or not, it will flow off easily. That property can be many things that we have, examples we have given. You just read through all that. Learn in this at least one or two in your own words. You don't need to use the same words and all, you can use it. So, say the property of viscosity is seen in the following example. Do the mass limit.
One, a stirred liquid when left comes to rest on account of viscosity. Thicker liquids like honey, water, glycerin, etc. have a large viscosity than thinner ones like water. If you pour water on a table, the water will stop soon and the water will flow up to quite a large distance. Second, if you pour water and honey in separate funnels, water comes out readily from the hole in the funnel, while honey takes enough time to do so. This is because honey is much more viscous than water. As honey tends to flow down under gravity, the relative motion between its layers is opposed strongly. Third, we can walk fast in air but not in water. The reason is again viscosity, which is very small for air but comparatively much larger for water.
Okay. Only one property is there. Viscous means more thicker. Viscous means more thicker, not easy to flow, and all that examples in daily life how to use it. So don't take time and by heart. So you need to know. That's why when PPT, like when you're not writing also anywhere, when you learn, don't waste your time in learning things which are not required. Got it? As I explained, if you're a person who forgets, go on writing. Date you put a later by studying, you just go through these pages. Don't study this, read only this definition. Like that, you can go on noting down. Because I feel you're wasting a lot of, like, here's so many other. I'm not going to ask you five applications. What? How much I'll ask? Max? 3? So any 3 you learn in, no need to even learn the same. Don't waste like 1 hour, 2 hours to learn all this word to word. No need to learn. You know words you can. Now this is a very simple thing called velocity gradient you're going to do. Okay. So this is what this figure is about. You have a surface, okay? You have different layers of liquid. Basically, layers are everywhere, okay? They're not broad. So there are different layers of liquid. This is the down part, okay? So let us consider random 2 layers. AB is a layer of liquid, and the next adjacent, that's very important. For example, for explaining velocity gradient, we're taking AB and the next layer CD, 2 layers very. Now, which will have more velocity according to what I told you just some time back? CD will have or AB will have? CD will have. So CD's velocity is V plus dV and AB's velocity is V. So how much CD's velocity is more than AB? dV velocity. dV more it has. Okay. Now, what is the distance of AB layer to the bottom? S. What is the CD layer to the bottom distance? X. Which is more farther from the bottom? CD. What is the difference in distance between AB and CD? Dx. So velocity of CD is dV more than this. Distance of CD, which distance? Vertical distance. That is, if the liquid is going like this, the vertical distance from the ground level, if you check, then CD has a little more distance than AB. How much is the difference? Dx is the increase in the distance. Okay.
No, but why do the top layers have like bigger velocity?
Because the liquid is not flowing in the same way. It is going in different velocities. But why you will check it's something else? Friction. I think it's due to viscosity. The friction and all that. Lower surface will be more and all that. So this is the full explanation. Okay. So here, consider a liquid moving slowly and steadily. Each layer moves parallel. The layer in contact is at rest where the velocity of all the other layer increases. That's what Nisha asked just now, no?
Yes.
Why is it like that? Yeah. The velocity of every layer goes on increasing as you go upward. Consider any 2 layers separated by velocity. So what is velocity gradient? Velocity gradient is change of velocity divided by the distance. So basically it is dV by dx. That is velocity. The difference in velocity between the 2 layers divided by the difference in distance between the 2 layers from the ground and from the surface. This quantity is known as the velocity gradient of a liquid. And this whole thing is clear. Okay. Next is, so we understood 2-3 things now. What is viscosity definition we understood? We understood in a liquid when it goes where it is 0 and there is maximum velocity. Then we understood what is meant by velocity gradient, which is dV by dx. And the next thing we are going to see is what is the effect of temperature on viscosity. Now, why it is on the molecular level and explanation for that and all, we are not going to do. If you are interested, you can go through later. You have to understand what is the effect of temperature on viscosity. Now, fluids have, which are the 2 types of fluids? Liquids and gases. Okay, both are coming under fluids. So, viscosity is something for both. For liquids and gases, you have viscosity. Okay. Now, what we say is for liquid, okay, velocity of liquid decreases with rise in temperature. That's the first thing you understand. If you take a liquid and you increase the temperature of the liquid, then what will happen? Viscosity. So, honey, if you heat, you take honey, and you heat honey, what will happen? It will become more like a water. It will not, that much thickness won't be there. That is the example. Viscosity of liquid decreases with increase in temperature. But for gases, it's opposite. Now why it is, molecular level, how it is and all, we are not going to the details of that. The syllabus, we are not going to the detail of that. So here what is it? Viscosity of gas, whereas, will increase with increase in temperature. The other one will decrease, this will increase with the effect of temperature on viscosity. You need to mention both because when we consider this whole chapter is about fluids, where gases also you have to mention liquids. So most of the thing we are talking about equation of continuity, Bernoulli, we have explained in terms of what? Liquids. We are explaining in terms of liquid. But here, effective temperature you have written in terms of gas and liquid. Next is what we have been talking about till now, coefficient of viscosity, eta. So learn it like this. Don't write like this, okay? You have to take like a small n, bring it down and curve it. This is what is known as coefficient of viscosity or eta. So we'll just see how this coefficient of viscosity or eta comes. Give me 1 second. Now, when I explained viscosity, I told you about the viscous force. What was viscous force? It is the tangential force which is actually opposing the movement of one layer on the other layer. Okay. So, this tangent, according to Newton, so Newton is the person who has explained this. According to Newton, the tangential viscous force is proportional to A and dV by dx. So, what is Newton saying? We have learned all three things separately. I told you. First, I explained what is viscous force F. Then I told about what is velocity gradient dV by dx, correct? And what is the area A? Okay, area of the liquid. So here the tangential viscous force F. What is Newton gave the relation between all the three. What is Newton telling? Newton is telling this viscous force has to be directly proportional to product of area and dV by dx. So V is proportional to area and dV by dx. The two things they say. So F is directly proportional to the area A and also the velocity gradient. Just now we saw what is velocity gradient between the different layers of the liquid, which is dV by dx. So if F is proportional to this, what will be F equal to? Proportionality becomes equality. What will happen with this whole thing? What is the extra thing coming? What is this? That's called constant of proportionality. So first he is telling F proportional to A dV by dx. Then we say F is equal to, proportionality became equality, so a constant eta A dV by dx. Along with that, what is there? A negative sign in there. Many places in the equation like this negative sign will come, and we'll explain why we have put the negative sign. So here also, eta is called the coefficient of viscosity. That constant is called the coefficient of viscosity, and negative sign shows that viscous force opposes the direction of flow. I told you that. Frictional force, if you push the body like this, tangential frictional force is acting like this. You push the body up, tangential frictional. Similarly, the liquid is flowing like this, then the viscous force is opposite. Viscous force is between the layers is opposite to the flow of the liquid. So just to show that F is opposite to the direction of flow, we put this negative sign. See whether you have understood it here. Look at that board and see. According to Newton, the tangential viscous force F acting on a layer is proportional to area A and the velocity gradient dV by dx. So F is proportional to A dV by dx. So F is equal to, now tomorrow you forget for exam, you wrote F is equal to eta A dV by, it's correct. There's nothing wrong about it. But negative is sometimes put to just show that eta, that viscous force is opposite the motion of the liquid. Now, so this is the equation. You saw here there is no negative sign. Now, in this equation, if A is 1 and dV by dx also becomes 1, then what happens to this equation? If in this equation, if I put A equal to 1 and dV by dx also is 1, then what will be F equal to?
F is equal to eta.
F is equal to eta. So that is what we are writing. This is how we define certain things. You remember what is 1 ampere? When you say 1 coulomb per 1 second. In 1 second, 1 charge, 1 coulomb flows, then the current will be 1 ampere. So sometimes for some definitions, we take some equation and say, okay, this and all is 1. then this will become, then from that we write a definition of what is 1 ampere or 1 joule and all that. Similarly here, we are trying to define coefficient of viscosity. So to define coefficient of viscosity, we already got viscous forces eta A dV by dx. So we say that this is called, so this formula is called Newton's formula. So Newton's formula for viscosity is what? F equal to eta A dV by dx. And the fluids obeying this formula are called Newtonian fluids. So there may be fluids, so anyone knows any fluid which is not a Newtonian fluid? Yeah.
Now there are few fluids that just got off, they got off the top of my head. One is called oobleck.
One is?
Oobleck. Now it's a material called oobleck. O-double-O-B-L-E-C-K.
O-double-O-B-L-E-C-K. B-L-E-C-K.
Yes, ma'am.
Oobleck.
And there's another one which is very simple to me. It's just a slurry of cornstarch and water. And
Cornstarch and
water.
They used to do in the science exhibitions and all they do. I don't know whether you know. Cornstarch and water when you do, it behaves very random.
Yes,
it's not a normal fluid. Yeah, that's
so
right.
what happens is when you apply urine force on such liquids, then the coefficient of viscosity increases so much that it almost starts to act like a solid inside the liquid.
They start acting as solid inside.
Yes, ma'am. And whenever the urine force disappears, it goes back to being a normal liquid.
So there are liquids. So any liquid which follows this is called the Newtonian fluids. All the fluids which follow this equation is called Newtonian fluid. So this is the equation. Now why did I ask you to put A equal to 1 dV by dx? What am I trying to define here?
Eta.
What is eta? So that we'll see in the next slide. So have you understood this feature? We just went to this equation, F proportional equality. Then we said if A equal to 1 and A, they are equal to 5. So this is the coefficient of viscosity. Okay. So we have the equation. I'll write down here. This is where we stop. Okay, so what is coefficient of viscosity? Look at the equation as I'm reading out the definition. Okay. Coefficient of viscosity of liquid. Okay, so from here, this is the equation. Is it correct? Yeah? Same here. Now, what is coefficient of viscosity? Coefficient of viscosity of a liquid, eta is equal to the tangential force. So, eta is equal to viscous force is only, this is coefficient of viscosity of liquid, eta is defined as tangential force, F, per unit area of the layer. What is per unit area of the layer here? A. A is the area of the layer. And what have we made A to? 1. So unit area of the layer. Unit velocity gradient means what? dV by dx we have made it to 1. Unit velocity of gradient. Normal to the direction of the velocity gradient is which direction? The dx is in normal or perpendicular to the direction. So that in terms like they are telling you coefficient of viscosity eta is equal to viscous force when area of the layer is 1 and when velocity gradient is 1. In words they have written that. That's all. Okay. So just look at this equation, this definition once again. Eta, the coefficient of viscosity, is defined as viscous force, which is a tangential force, when you had the area of the layer per unit area of layer and which had a unit velocity gradient. And how was the velocity gradient measured? It was normal to the direction of it. That you understood, no? Layer is going like this, dx is measured perpendicular, normal to the direction. So that is what is definition. So learn the definition of coefficient of viscosity. So other things and all will not come, this will come. Define coefficient of viscosity of liquid and give the equation. So eta is equal to F into F by, so eta is equal to F by A into dy by dx. Clear? What is coefficient of viscosity? Now it comes only different units and direction from it. It's a little different confusion is there in the units, but it's all, I tried to write it again and again and make it clear, but it's simple. You just have to go one step after the other. So till here, any doubt is there, you ask, then we go to the next step. It's clear? Clear? What are we talking about? Eta is equal to F by A into dV by dx. Now let us see the dimensional formula. You know how to do dimensional formula. So tomorrow in your final exam paper, I can ask you, give the dimensional formula of coefficient of viscosity. Fine, and already you know the equation. Let us see. Force. What is the dimensional formula of force?
Mn
e raised to minus 2, which is mass into acceleration. Area is what? L square, meter square. dV is what?
by T.
Velocity, so L by T. And dx is what? Here, force A dV L by T and dx. If you put together, you get m L raised to minus 1, T raised to minus 1. This is the dimensional formula of coefficient of viscosity. That you get it from the equation of coefficient of viscosity. Okay. So it will be explained. Now we'll see the different. Now it's so many units you know, like Newton, Joule. I think all of you know most of the units, SI unit, CGS unit you have learned. Now here, viscosity is units you're going to write down. Okay, you're writing down the different viscosities unit, the interconnection and all that. You go slowly. One I will do, then I'll ask you if any doubt is there, then only I'll go to the next one. If not understood, just raise your hand. So we have to use our base equation is this, okay? Yeah. So force. What is the CGS unit of force? CGS unit of area. CGS unit of dV by dx. Now dV is meter per second, centimeter per second, correct? dV, velocity is centimeter per second. And what is the unit of dx? So what is the unit of dV by dx? Clear? The dV is centimeter per second, dx is centimeter cancel. 1 by second is second inverse. So dV by dx unit is second inverse. So is it correct to write like that? Yeah? So write down di centimeter inverse to minus 2 goes up minus 2, minus 1 goes up as plus 1. Now this whole thing, 1 dyne per centimeter square second is given a new name like Joule, Newton. What is 1 Newton equal to?
1 Newton is equal to 1 kg meter.
So instead of filling everywhere so much kg meter second square, so much kg meter per second square, we have defined the new name Newton. Similarly, Joule we have like that. Okay. Now this 1 dyne centimeter inverse to second has a new name. It's called poise. So poise is a CGS unit of viscosity. Poise is a CGS unit of viscosity. Till here, just look at this because we will repeat this for S. We will repeat this for SI unit. So there should not be any confusion. This is our basic equation. So this you learn now. This will come under equation for coefficient of viscosity. If I ask, you can use definition of eta. You can use this. Units of eta. You can use this. For everything, this is our basic equation. Now we'll go to SI unit. Okay. Now SI unit. Look at the equation on the board there. What is the SI unit of force? What is the SI unit of area? And what is the SI unit of dV by dx? Per second. Is it correct to write 1 Newton by meter square per second? So 1 Newton, this 1 Newton meter square per meter inverse to second can also be written as Pascal second. Is it like this or is it like this? Pascal. Pascal. Do you write Pascal as suffix A? No. This is like a suffix. You write the same line. Pascal, how do you write this? P and A. Yeah. Pascal second. Okay. So here, it's Pascal only. Pascal second. So they have just written like this. Don't learn like this. Learn like this. Normal Pascal. What is 1 Pascal equal to?
1 Newton by 1
Newton meter inverse 2, correct? So this Newton meter inverse 2 is Pascal and second. It is not Pascal per second, it's Pascal second. Okay, if you have confusion, you can write like this. Pascal second is one dash. Okay, so so you got CGS unit is 1 poise, okay, and you got SI unit as 1 Pascal second. Now what's the relation between poise and Pascal second? Okay, so that's this whole thing. Okay? This you don't know. Okay, I think I've just rewritten in my own handwriting because I felt this is more confusing. The same thing I have written here. Okay, the same thing I have written here. I'll show you how it comes. So if you understand this, you can go back and learn it's the same. So this is what we saw just now. Is it correct? 1 Pascal second is equal to 1 Newton meter inverse to second. This is how I told you. You should write Pascal here like this. Now, hand side, you keep it like that. What is 1 Newton equal to how much dyne? Is it correct to write like this? 1 meter inverse 2, can I write it as 10 raised to minus 4 centimeters minus 2? Is it correct?
Yes.
Yeah. So, 1 meter inverse 2 can be written as 10 raised to minus 4 centimeter inverse 2. And second is second. Okay. If you have a confusion, learn it. 1 meter is how much centimeter? 10 raised to 2. 10 raised to 2. So, 10 raised to 2, then raised to minus 2. Do like that and you get that. Okay, 10 raised to minus 4 centimeter inverse 2. Now, here, you take this equation. Now, what is 10 raised to 5 into 10 raised to minus 4?
10.
10. And remaining dyne centimeter inverse 2 second, dyne centimeter. Now, in the previous slide, what I had taught you as 1 dyne centimeter inverse 2 second called as
1 poise.
1 poise. So, 10 and this whole thing is poise. So, 1 Pascal second is 10 poise. 1 Pascal second is the SI unit of viscosity. Is 10 times of the CGS unit of viscosity, which is poise. So, this can also be written as 1 Pascal second is 1 decapoise. Deca is another suffix used for 10. Okay, deca is another suffix used for 10. So, if you write like this, from here, if 1 Pascal second is 10 poise, then what will be 1 poise equal to?
1
by 10 Pascal second, correct? 1 by 10 Pascal second. What is 1 by 10 Pascal second? 0.1 Pascal second. So 1 poise is equal to 0.1 you can write here, and Pascal you can bring it back and use it. We are just going like this, round and telling many relations. So if you are getting confused, wait, they're not okay. So if you are, first thing you sit, go home, see whether you can understand all this, okay. Second thing, what you will be learning is, learn this. This is clear? Learn this. This is also clear? Okay. And then just learn that 1 Pascal in this most important would be, what is in the box? Can you see? I put 2 boxes. Learn these 2. More like that. If you're finding it difficult to get how it is and all that, just learn this one, and this one. Okay, 4 things you learn and keep. If you can get the relations, it's just rearranging SI Newton to dyne, centimeter to meter, going up and down, you're doing that's all, nothing else. Okay? So take some time and learn that. Now this is the most important derivation of, this is the most important derivation of viscosity. 100% sure question for your unit test, first term exam, final exam and all that. Derive the Stokes formula. Stokes formula is an equation which is derived for viscosity. Viscosity equation it is. It's called Stokes formula. So you have a figure which you have to draw for exam. Now don't take 1 hour to draw this all the dash like this and all that. Okay? You don't have to draw anything. So suppose it's for exam, you can just draw. For exam, you can just draw and look. That's all. Maybe that's enough. This whole dot is just showing in a liquid the sphere is moving. You don't have to waste your time to draw all the dots for the liquid. This much is enough. Okay? Let us understand what it is. So you have, this is actually done. We used to do it in the lab for our science project. Our physics project before, like some 10 years back, used to be, you have to actually do something, not like writing. You have to do some experiment in the lab. So what they did was, I don't have the tube now, they have this long vertical tube of this height. Okay, so this height tube will be, is like a long glass jar. In a calorimeter you measured, no, one jar. That one's big for so much height and so much only round to be so much. Okay. They fill that with the liquid, oils and water and all that. They fill it with some liquid. And they have this steel ball bearings, spheres, small spheres there, not big ones, small ones there. And what they'll do is, they'll have a stop clock. At the top, they'll just drop this. Okay? From the top, we drop this. At a particular point on the tube, they mark one marking. When the thing reaches there, you switch on the stopwatch. And then when the thing hits the bottom, you switch off. So you get a time of travel of that ball bearing from top to bottom. Using the time of travel of the ball bearing and the distance, how much it has traveled in that time. So you know the top distance and down distance. And you know the time. Knowing the distance and the time, can you calculate velocity? Yeah, you can calculate velocity. From the velocity of which the sphere is going, you can actually calculate the value for coefficient of viscosity of the liquid. So they'll do it experimentally, they'll find out coefficient of viscosity of the liquid and they'll find out that. And they will have the chart. See, we have all the values of coefficient of viscosity in many places, like in all the, you have this refractive index of liquids and all that chart, no? Like that you have it even coefficient of viscosity. So from that they will verify this guy. Say suppose I got viscosity as 10 for some liquid and actual viscosity is 50. So I'm very close to it. Okay, I've done the experiment time. Suppose I have got 10 when the viscosity is 200. These are not that right. So they will do that percentage error. Nice experiment. It takes time because once you fill it with oil, you have to wash it with that. Then only you can use the other oil. And such a long glass tube. It's a glass, this one. Just to be poured water and all that. No? So we used to do it. So that experiment, how do we actually do the experiment at coefficient viscosity? That coefficient viscosity equation is derived using the Stokes formula. So here the liquid is there. You're dropping the sphere in the liquid. When the sphere is dropped in the liquid, what are the different forces acting on the sphere?
There's a gravitational force.
Wait.
No.
Okay, so here, what are the different forces acting on the sphere? So this is a sphere. So that first you understand. This is not a water drop. It's a sphere, actual solid sphere, okay, which has a density. It can be a steel or any other material. So that's a sphere. The first thing that acts is mg, weight acting downward. Correct? So this is one of the forces which that. The velocity with which the sphere is coming down is v. It's not a force, so I'm not circling it. It's v is the velocity with which the sphere is coming down. Next. Can you tell me what is this?
Buoyant force.
Huh?
Buoyant force.
What is it called in viscous force. Friction or viscous force. Any force which opposes the motion of the sphere through the different layers of the liquid, it is acting upward opposite is viscous force. And this is what we have left, that small portion I told you, I left with that upthrust or buoyant force. Upthrust or buoyant. From anything you put inside water, from the object has an upward force on the liquid which is known as the buoyant force. Okay, so this is the buoyant force. So you have U is the upthrust, should be opposite the motion. F is the viscous force and mg is the weight. Okay. When the sphere is in equilibrium, there are three forces acting. Two are upward and one is downward. So when we put the sphere in the tube like that, it's a small sphere. First initially if it is going fast, after that it goes with a very constant velocity. So when does something go in a constant velocity? When many forces are acting.
Net force is 0.
Net force is 0 or the forces are balanced or they are in equilibrium. So what is the total upward force?
U plus F.
And what is the total downward force?
Mg.
W, which is mg. Okay. So when U plus F is equal to W, when the upward force has exactly balanced the downward force, U plus F, upthrust and viscous force, is exactly equal to W acting downward, then you find that the sphere is under 0, that is net force is 0. So acceleration is 0. When something's acceleration is 0, the body can either be at rest or in uniform motion. That is why it goes with uniform. And the velocity with which the body will go like that, when these three forces are balanced, that is U plus F is equal to mg, is called terminal velocity. So terminal velocity is not the velocity of the sphere. You can't say that. In the initial point when it's not beginning when you put within a fraction of seconds happen, but till that time it's not constant. So that time it's not terminal. Terminal velocity is the velocity of the sphere when acceleration of the sphere is 0, when the net force on the sphere is 0, and when U plus F is equal to W. Yeah. So that is what is this. So that is what this whole thing we have written here. Okay. Now we will get an equation of U. I will have an equation of U. I'll have an equation of F, and I'll have an equation of mg. And then all the three will combine. And what is my main A? Eta. What is eta? Eta will come from which equation? It will come from F equation. So this viscous force has a particular equation. Again, I'm not deriving the viscous force, how I got that equation. Like F equal to mv, you know how it is derived, and I'm telling you that is. W equal to mg also, you know, mass into acceleration. So but like that viscous force is one equation, right? That I'm not going to tell you how. I'm not deriving. But we're using it to find the eta equation or finding the Stokes formula. So we'll just read out this whole thing.
opposing force also increases. The state is reached where the upthrust of the fluid and the viscous force balances the weight of the sphere acting vertically downwards. Now the resultant force is zero and the body moves with a constant velocity. This velocity is called terminal velocity.
Yes, that's all. What is about the terminal velocity? Now it's just math. This is the basic understanding of the figure. So when you write for an exam, I would expect you to draw the figure. And a small explanation need not be the same words, at least a few. Like this will be very good. I remember one year, last year, everything was written till here. No one wrote resultant force is 0, so the body is going with constant velocity. That is the key. If you don't write it in the beginning one, this should be there. That the resultant force is 0, so the sphere is going to go inside the water, inside the liquid with a constant velocity called the terminal velocity. That was just the equations. So this is where we start. This is what I told. Clear? You remember this? U plus F is W. So you have a sphere. U is upward, F is upward, W is downward, and the body is going down with velocity. So three forces. Okay? So U plus F is V. Now this F is called the viscous force, which is given by the equation 6 pi eta AV. Viscous force. So I can ask you, define viscous force and give the equation. I already explained what is viscous force, a tangential frictional force inside when the layers move. That have already you have the definition. What is the equation called? F 6 pi. This derivation we are not having. So let us understand the terms. F is viscous force, you know. This constant. What is eta? A radius of the sphere which is coming down here, and B the constant velocity. B is the terminal. So you understand what is 6 pi eta. So where F comes, we can substitute 6 pi eta A. And what are the two things we need? We need W, correct? We need W. Now what is W? Weight of the body acting downward. W is equal to mg. Now this G, you write it here. Can I write mass into volume into density? Mass is equal to volume into density. Can you tell me what is V here? Volume of what?
The ball.
Volume of?
Volume of the
Sphere. Volume of the sphere is V. What is rho?
Density of
Density
the
of?
The liquid. The sphere.
Sphere. Density of the sphere. Sphere is a material, no, I told you metal, steel or brass or whatever. So here you can understand, because I am going to talk to you again after next one of another density sigma. So you should be very clear which is what density. So when I talk about W, I am talking only about the sphere. Don't even imagine it's in a liquid. So W is weight of the sphere, which is mass of the sphere into G. Mass of the sphere is volume of the sphere into density of the sphere into G. Clear? So what is the volume of the sphere? Pi A cube. We'll take it as A. A is the radius. And rho is density into G. Okay. So, yeah, this equation. What is A here?
Radius.
Radius of the sphere. Rho, density of the sphere. And G, acceleration due to gravity, 9.8. So we got F is equal to 6 pi eta V. We are ready with that. We got W is equal to 4 by 3 pi A cube rho G. We are ready with that. Now what is the thing that we need? U, and we have not learned U. U already have left. Okay. So we just write the equation of that. This upthrust, U is called the upthrust. We'll derive an equation for upthrust. At least you understand from what I do what is upthrust. Yeah. Upthrust is defined as weight of the displaced fluid. That is, if you take a liquid, okay, and you have a sphere inside a liquid, you have a sphere inside a liquid and the liquid is there. There is an upthrust because the sphere is there here. It's an upthrust which is acting upward. That upthrust is equal to the weight of the displaced. So the sphere has come to the place where some liquid was there. So some liquid has got displaced. That is why the sphere is there. Correct? When I put the sphere here, when the sphere is moving, what is it taking the places of? The liquid which is already there. So when I say upthrust, upthrust is equal to weight of displaced fluid. That means where the sphere is there, some fluid has moved off. From there, that only the sphere came inside there. That weight of that is equal to upthrust. Okay? So let us do that. What is the weight of the displaced fluid? Can you tell me what will be the shape of the displaced fluid there?
Spherical.
Same sphere. That how much is the a sphere that is there, that much liquid has only gone off. That much is the shape also is a sphere. So, what is the weight of the displaced fluid? Weight of the displaced fluid is mg. Mass of the displaced fluid into acceleration to gravity. What is mass of the displaced sphere? Displaced fluid? Volume.
Sigma.
This is one, which is equal to mg, which is equal to volume of the displaced liquid. Correct? How much again? Density of what now? Liquid. The sigma here is density of the liquid, because we're talking about the weight of displaced liquid, not of the sphere. Okay? Volume into the energy. Is it correct? V sigma g. Now, what is the volume of the displaced fluid? Is the volume of the sphere. Correct? Sphere has come and taken the place. No. So, 4 by 3 pi a cube is the volume. Sigma. Is it clear how I got this equation? 4 by 3 pi a cube sigma. So, first if you understand this, have you understood this? Then you understand about what is the weight of the liquid displaced. We'll write it here again. Weight of the liquid displayed is mass of the liquid into g, is volume of the liquid into sigma into g, which is 4 by 3 pi a cube sigma g. Clear? This is correct. So this is W. I got an equation for W. I got an equation for U. And I got an equation for F. So I just add all the three equations, I substitute and rearrange. What am I trying to find out? Equation for what? U. Equation for eta, coefficient of viscosity. The whole thing is about Stokes formula, which is equation of viscosity. So here, just rearrange. See. So if you learn, for example, you are learning for exam. Here it's a very confusing thing. Can you see? Like that, we go step by step. Directly learn of U is weight of displaced fluid equal to 4 by 3 pi a cube sigma g. No need even to show me. So then one step is over. Easy. Then you can just substitute. So what is this? F is this, W is this, and U is this. So 4 by 3 pi a cube rho g minus 4 by 3 pi a cube sigma g. Common term you are taking now. So if you want to write like this. Take it common, simplify. Now this to this, I am not showing it on the board, you go home and do. Just maths, okay? What do you have to do? You have to take 6 pi AB, you have to bring this side, then cut the common terms and do all that and all that. You will get this again. This is called the Stokes formula. What is it equal to? Eta is equal to 2 by 9 a square rho minus sigma by dBj. What is eta? Coefficient of viscosity, which is a constant for every liquid. Like coefficient of viscosity of water is so much, honey is so much, oil is so much. So that is eta. What is A?
Radius.
Radius of the sphere that you are dropping inside that. Then what is that inside the liquid? Rho.
Density of the
Density of the material of the sphere. Sigma. Density of the liquid in which the sphere is moving. V. Velocity. That is terminal velocity, not any velocity. Terminal velocity. After all the forces balance, what is the terminal? So from this I can also calculate terminal velocity. What will be V equal to? Is it correct?
Yes.
No? So I can say, or if I ask you derive the equation for terminal velocity, I am not asking you to derive the equation for it. So you reach to here, then you just substitute V, you bring it here, eta you bring it, and write the last step as V equal to 2 by 9 a square rho minus sigma g by 9 meter. So that's this. So according to Stokes formula, the terminal velocity, so we can get V equal to 2 by 9. Same thing. See here, in this equation V brings, you bring V this side and eta this side. Okay, so you will get 2 by 9 a square into the vector. That is all. So what's the relation between V and A? V and A, they are directly proportional. So the terminal velocity has a direct relation to radius of the sphere. Terminal velocity is directly proportional to radius sphere. Now these are the assumptions made by Stokes. So learn at least 2-3 assumptions. What when when they do this experiment, okay, in the tube, the sphere is dropped. These are the following assumptions which Stokes made. Then only this is perfectly correct. So some of the assumptions may not be correct. That's why when you do experimentally, you will never get the exact value. There will be a lot of errors when you do the experiment. So if it is 10, then you will never get 10. You will get 8, 5. You will never get 10 because you have to follow all these to get that 10. Okay. So let us see what are the assumptions. Yeah. Aditya Koshika.
Yes. Stokes' for assumptions. 1. The medium such sphere falls is infinite in extent. 2. The spherical body is perfectly rigid and smooth. 3. There is no slip between the spherical body and medium. 4. When a body moves to the medium, no any kind of waves should be set up in the medium. 5. The body must move to the medium slowly. The terminal velocity of the body must be less than the velocity of the medium. 6. The medium is homogeneous. The diameter of the spherical body must be large compared to the spaces between the molecules of medium.
So many other assumptions. You can learn at least 2 or 3 and keep what are the assumptions made by Stokes. Next is what is an application of Stokes' formula? It's a little complicated because I had to do it because in Newton what they did is from here somewhere they went, then they didn't show any of this and suddenly they wrote off an equation like that. I remember while writing last year only, or the COVID time when I wanted to make this slide. We were checking, they didn't do that. So that is why in my own, I have written into a paper and solved and given. So it's simple only. You just see whether you can understand. So this is basically Stokes' formula, parachute. What happens when a person falls? Why does it suppose there's an airplane, a person falls off from an airplane, will come and hit the ground with that velocity, very high velocity and will die. Why is it that parachute when you come, why is it that the person does not fall like that? It comes with that it comes with a uniform velocity, like a terminal velocity. So you should understand that here the man with the parachute is like the sphere. And the liquid that the sphere is going is the air. Okay, so what will happen when the sphere is dropped in the liquid? The sphere is not coming with increasing velocity. What is happening to the sphere? It is coming with a constant velocity. What is the velocity called? Terminal velocity. Just like that here also you will see that the man is coming down with a constant. That is why he doesn't get hurt. He is coming with a small constant velocity and he just reaches the ground. So let us see the equations. So consider a person with a parachute jumping from a flying aeroplane. He descends very slowly in the air. He doesn't fall off like that. He descends very slowly in the air. So G dash is we define as effective acceleration of the falling parachutist. So what is the effective acceleration? Total acceleration acting on the parachutist is G dash. Let M1 be the mass of the man with the parachute. You have a man. You have a parachute. Okay. So the man plus the parachute's mass is M1. What is M2? Mass of this air inside the parachute is M2. So what is the total mass? Man, parachute and the air inside the parachute. Okay. So mass of the man plus parachute is M1. Mass of the air linked with parachute means inside the parachute. Parachute is not, this air is there. You have seen all of it. So mass of air linked with the parachute. Now, force is mass into acceleration. That's the only equation we need. Okay, so F is equal to ma. Whatever be the F ma, this equation will always be true. So here, F is net force acting on the parachutist has to be equal to total mass m1 plus m2 into G is G dash. So net acceleration due to gravity on the parachutist has to be equal to net force acting on the parachutist by total mass. So here, now G dash you keep it as G dash, m1 plus m2 you keep it as m1 plus m2. So we are going to see what is the net force acting on the parachutist. Okay, we are going to write an equation for the net force acting on the parachutist. What is the net force acting on the parachutist is, you have I told you, imagine the tube liquid as air and imagine the sphere as the man with the parachute. Okay, so the sphere. What are the different forces acting on the sphere when it falls in that tube?
Okay.
So the man is coming down. So what was acting up? Viscous force, Fv, F was there, and then you said about upthrust U. So we have written before U and F. You remember upthrust upward and viscous force. This viscous force we will call now by Fv. And this upthrust we will call by Fb, which is buoyant force. So our buoyant force, upthrust are same. Okay. So you just imagine that if you had a tube with a sphere, you had the viscous force and upthrust and the was coming down. If you have a man with a parachute, okay, this force, viscous force, is given a new name Fv. This upthrust is given a new name buoyant force, and the man is coming down with it. Is there any difference? No, it's the same thing. Only the names are changed. F is called now Fv. Upthrust is called by buoyant force Fb, and the man is coming down with what velocity? A constant terminal velocity. So here. Yeah, so what is F net equal to? And what is the net force acting on the man? What was the net force acting on the sphere? What is the relation? What is? Mg minus F plus U. Okay. So Mg minus F plus U is the net force. Similarly here, Mg, full man, parachute, all mass together. Weight Mg minus Fb plus Fb will be the net force acting on the body. And that by M1 plus M2 is equal to G dash. Now, let us write down this. Shall we write down somewhere? G dash is equal to net weight of system, that is man, parachute, everything, minus Fb plus Fv by M1 plus. So we will get an equation for this. So what is Fb? That the buoyant force. Now you have to understand there's an equation for buoyant force as V rho G. We have not learned. Okay. Buoyant force is, in the earlier one, what was buoyant force? Written as upthrust equal to, what did I teach you? Upthrust is equal to what? Weight of?
The liquid. The weight of the liquid displaced.
Weight of the liquid displaced is upthrust, I told you. Similarly, even buoyant force or upthrust can also be written as V rho G. Okay. Now, rho and G you keep it here. What is V? Volume. Volume is mass by density. So, M air by density. So, what is the air which is linked with the parachute? It's called M2. So, M air is M2 by rho into rho G. Rho and rho cancel, M2G. So, what did you get FB as here? M2G. So, FB is M2G. Keep it there. Okay, next. FB. Okay, here we assume FB is taken as 0. FB is negligible. Viscous force is what? Viscous force is the force acting on the man in the parachute. When he is coming down, force is acting up. Since air is very less viscous, air is not a viscous fluid, so we neglect FB. We say FB is 0. So this FB we take it as 0. See, have you written? Viscous force is assumed to be 0 since parachute is coming down with a very low velocity. It's coming with a low velocity, and viscous air is not a very viscous fluid. So we make FB 0. So what are we left out? So G dash is there, M1 plus M2 is there, here one M2G is there, here one 0 is there. What is weight of the system? What is the weight of the man plus the parachute? Is M1 plus M2 into G. So just substitute. What is it? G dash, G dash is equal to weight of man plus the parachute plus the air inside the parachute. All together, what is the weight? M1 plus M2 into G minus FB. What did I write FB as? M2G. FB is 0 divided by M1 plus M2. Simplify, you will get G dash is equal to M1 by M1 plus M2 into G. So what is this G? Acceleration due to gravity 9.9. And what, does the man feel the same acceleration? This is the acceleration with which the man is coming down. So what is the acceleration? G dash, effective acceleration is M1 by M1 plus M2 into G. So that's all about that. Okay. Here, next is this explanation you need not learn. I just explain the graph. When you have
Go to the previous slide one more. How did you get the final formula?
From this simplified m1g plus m2g minus m2g. M2g cancels. So m1 by m1 by m1 plus m2g. Now here, this is a little confusing. Don't read this. Learn this graph alone. It's a BT graph for a sphere coming down in a tube. Okay. Now, the moment you put the sphere in the tube, inside the liquid, what is happening to its velocity? It's increasing. Then, when three forces balance, U, F and W all balance, after that what happens to velocity? Becomes a constant. That's all you need to understand. Okay. So here, you have a velocity and time graph. When you started, when the sphere was dropped into the tube, at that time velocity is increasing for some time. Not for a large time, for some time. And then after that, when all the forces get balanced, the velocity will become a constant. So you know, just learn the graph and just understand that when a sphere is dropped in a liquid, for some time the liquid, or some time the sphere's velocity is slowly increasing. As in the case of parachute also, the man will first fall in the velocity. When the parachute opens, all forces are balanced, it starts moving a constant velocity. So it goes constant. And the next one is, this is the only slide. Now here, lot of things which are not there. Okay, drag coefficient, you're not deriving anything. You're just understanding and just writing the equations. What is drag coefficient? Okay. So terminal velocity in terms of drag coefficient, you will see what it is. So in the case of, I'll just read out one paragraph. In the case of large objects, so we're talking about, in the case of large objects like skydivers and aeroplanes, the resistive force is approximately proportional to square of the speed and the resistive force or drag force. Now, how did we get the drag force? We are not deriving. We are just writing the equation for drag force. Drag force means it is an opposing force. Okay, it's an opposing force. You can even say, see, if something wants to go forward, suppose an aeroplane wants to go forward, there's a force which is opposing the movement of the aeroplane. Or something is falling down, and there is a force which is opposing, like our viscous force, something similar to viscous force. Okay, that opposing force is called, it's dragging you behind. It is opposing you from going forward. So it's called resistive or drag. It's a resistive or drag. So if an aeroplane is going like this, the drag force is like this. If something is coming down, then the drag force is happening. Okay. So that drag force is given by the equation D equal to half C rho A B square. Now this equation we are not deriving. So we're just learning. Just understand the concept that if something wants to move in a liquid forward, there is a resistive force which is opposing the movement, and the equation for that resistive force is half C rho A B square. Now what are these things? C is a dimensionless quantity. It's like a constant. Rho, what is rho? Density of air. So the body is going in air. Okay, so rho is the density. What is A?
Effective velocity.
Cross-sectional area of the falling object. So if you're taking here, you're talking about falling object. So the object is falling like this. A is the cross-sectional area of the falling object. C is a constant. And rho is the density of this air. Rho is the density of air. So and V is what? V is the velocity with which the body is coming down. Yeah.
I'm not about the effective cross-sectional area. Because
Effective cross-sectional area may be, suppose this is falling, maybe this is the effective cross-sectional.
yes, ma'am. Ma'am, but I think it's the effective cross-sectional area because it can fall in different positions, right, ma'am?
It can?
Fall in different positions.
Yes, yes.
So when the cross-sectional, when it falls like this, the effective area will be just this, right? When it falls like this, it will
Then
be
that
much
is it,
more.
yeah. So what he's trying to say is, suppose you have something is falling like this is the effective cross-sectional area. Falling like this, so which is facing the thing which is coming down. Okay. So till here. So what is F? F net force acting on the body. So something is falling down. One is always acting downward. What is always acting downward? Weight. It's weight, Fg. And now I have talked about what? A drag force. So what is the net force acting?
Mg minus
Drag force. So F, the net effective force is Mg minus the drag force. It's Mg minus, substitute this drag force from here. So F is equal to Mg minus half C rho A B square. And what is the net force acting on the body when a body is coming down with constant velocity? 0. So this is equal to, so we have written mg minus half 0 a v square has to be equal to 0. So from this we can calculate what is Vt. You rearrange the terms and you get Vt is equal to 2 mg. Now here have we taken into consideration upthrust?
No.
Have we taken into consideration upthrust? What is the only thing we have taken into consideration?
Drag.
The drag force or like a viscous force, equivalent to viscous force 1.
Ma'am, so what's the difference between the upthrust and upward frictional force and drag force? Because they're all the
Upthrust
same
is
thing.
because of a phenomenon of anything in any liquid. There is a upward thrust
Only
of the
liquid
body.
or fluid?
Fluid. Okay, that is upthrust.
Yeah.
Viscous force is completely different. It's a force which is acting because of the relative motion of the layers. So whatever still, you could have dropped a sphere. So when the drop is going down, the layers have moved. So relative positions of the movement of the layers, because of that force is only viscous force. But the upthrust is, even if it is not going a sphere you put inside the water, there is an upthrust. Something you dip inside the water, there is an upthrust. So upthrust and viscous force are not same.
Okay, what about upthrust and drag?
Drag is similar. That's what I'm saying. The drag is very similar to either an upward force or a viscous force and all that. Together you can think about a force called drag force. So it can be a different, according to me, the viscous force, upthrust all together, the only total force which is opposing the motion. That is nothing but upthrust plus viscous force. That is only can be called as the resistive force or the drag. How we got the equation, if you see the derivation, then you can understand. Maybe they start off there and end here. So you can just check what is the derivation of drag force, how do you get that. Not in your textbook, it's not there in your textbook. It's not.
So that is the drag. And it's a bit complicated because it involves a lot of integration.
It involves a
A lot of integration.
That's what I'm telling you. It is not, it may be not, it may not be at the scope of your level. That's why they're not talking. They're just saying drag force and drag force. So, have you, after seeing, in this only, one second. In this, the only unknown thing is how you got the drag force. Other things are very clear in this. The total force opposing the motion of the body when the body comes down is called drag force. Equation for drag force is this. The net force acting on the body is the downward force mg minus the upward resistive force. D is written from here like this. When the body is under equilibrium and it starts coming in constant velocity, then the upward force and the downward force are same. That is why this whole thing becomes equal to 0. And this V that we are talking about, this V is the constant uniform velocity with which the body is coming down. And that is called the terminal velocity, and you have an equation for the terminal velocity. Root of 2 mg by C rho A. Okay. So I'll just, this is the, Anil is not there, he gave this one here. Okay, look here. We finished 1 and 2 I have uploaded yesterday. Okay, sorry. 1 and 2 we have uploaded yesterday. 3, I told you 1 extra will not be done now. We have time to do it in January. That is basically this only. That time you will understand very clearly. Upthrust. Why I wrote upthrust is V rho G. Why I am writing upthrust is weight of displaced liquid. That clearly. Okay, that we are reading now. Then 3 and 4 we just finished. Next is 5 and 6. The 2 PPTs are there, 5 and 6. It basically talks about capillarity, capillary tube, then something about pressure difference in a liquid and all that. So we'll see tomorrow. Tomorrow, 2-3 things I want you to remember. First, I want all of you to bring your homework book tomorrow. I'll put a message also. Just submit your homework. I'll just check whether everything is marked. For some, I have not checked yet. Okay. So homework you submit. Classwork, of course, I think I have marked everything and all that. If you want, I'll tell you. Okay, classwork will be done. Homework you all submit tomorrow. Whatever state, whether it's corrected or not corrected, you submit. Then project is for 13. No asking, begging, why it is not there, hundreds of reasons, nothing. Already only 2 children have taken permission, but those are traveling, 1 or 2 have taken permission from the parents and called up and told. Others are all 13th onwards, a mark will go out of 10. Now, 13th you submitted, but everything is something you know you have done, you have not followed instruction, you have done half left, half there. You give me, I give you 5 out of 10, or 13th also if you submit, I give you only 5 out of 10. So, mark is out of 10 on that submission day, but then again, all the instructions are they followed? Have you followed how I told you how to write, what are the order I told you to get? Have you followed all that? According to that, marks will come. and on 13th, or we'll keep it on Friday, you submit your first term paper.
Yeah.
With questions written. I don't want only the answers. Questions have to be written. Explanation has to be given. Explanation of figure may be written in the answer key. You have to write the explanation of the figure. Derivation of the equation, if it's written, you have to derive. In that, if you leave many things, figure is not drawn, half a year left here, half a year left there, I'm not going to give back. I'm going to give you a mark out of 10. That mark is going for your final exam, first term paper that you solve. Okay. So if you do many incomplete things in that first term paper, because you don't have to worry about the answers, I've already sent you the answers. You just have to copy it. Some explanation, 1 or 2 where I've written explanation, you can refer the PPT and copy. If you leave that there also out of 10, I will give you mark 5, 6, 7, 8, 9, 10. Different mark will come according to what you have written and kept in that solved paper. Give it on Friday. Friday.
I think for this, in your PDF, question 17 was missing. Like, yeah, the derivation of banking of
because what happened is, by some error, vector product 2 times I wrote.
Yeah.
And I wrote the answer key also, I don't know how, because I read it different times. Once I made question paper, then after one week, my memory is bad. Later I saw vector product is in question 1. Is that again I am seeing vector product, 2 questions, same question. Then I cut off that and I made banking of road. So if banking of road is not there, you have to write it yourself. You write yourself the banking of road. I think I later made that correction to my answer key. Maybe it's missing. So banking of roads, whatever is asked, you take your PPT and check it. Okay. So that also take the full effort to sit and check the answers. Marks are there for both. Okay. Again, that also submission on Friday we are keeping, because tomorrow I give you the paper. Check your paper, clear. Please understand your mistakes. That's first very, very important. It's not at all about the mark. You understand your mistakes so that you don't repeat the same. Okay, that is the reason. First time in the history of, I think, 18 to 19 years I have taught in Bethany. First time I corrected the practical in the lab. I have never corrected the practical in the lab. Last year also I have not corrected. What happens is, even your seniors, when I tell, now tomorrow I will say, in the lab that day when you did, you should have done that. Will you understand anything? Will you remember anything? No. But that day I told you, many of you have told why I have cut the marks, why your marks have been lost. So practical, we will not be discussing anything tomorrow. I'll just give you the practical paper. You've already seen your practical paper mark. You know what is a mistake, and that's the reason we did that. But theory, there will be a lot of doubts why you got this mark. But understand why you got it wrong, you come and ask me, I'll tell you. So that you don't repeat that for your next unit test or first term or next 12th standard anyway. Each time you write an exam, you should understand next time you should never repeat the same mistake. Suppose you knew a figure but you didn't know that figure has to be drawn. You made a mistake. The next time you know, I didn't draw the figure, I lost mark, so I should draw. So tomorrow we'll do that discussion, and tomorrow I think there's no practical. Monday, Tuesday is what I remember. So practical, you had to bring that simple pendulum, correct? Why don't you finish that calculation and bring? So when you check your paper, I'll correct the simple pendulum observation. Bring the simple pendulum observations. Okay,
Ma'am, numbering of pages for project should be like on the right hand side, like is it
on the written side?
Written side, like center, border.
I told border right in the center, but if you have made like side is fine for this time. But when you are in 12th, I'll tell you exactly. I want it in the border, middle down. If it is like that, leave it. Suppose you have already printed top or corner, or don't sit and change, leave it like that. Bye.